Hello there and welcome to Physics with William, where curiosity can slow down, the lights can stay low, and science is allowed to take its time. Tonight we're going to look at a question that seems simple at first and becomes stranger the longer you sit with it. Why does time have a direction? Most of us never need to ask this. We wake up, move through the day, become tired, go to sleep and begin again. Breakfast comes before lunch. A dropped cup falls before it breaks. A candle burns down rather than building itself back up from smoke. We remember what happened yesterday, but we do not remember what will happen tomorrow. Everything appears to move in one direction, and because it has always felt that way, we tend to treat it as obvious. But physics is rarely satisfied with something simply because it feels obvious. Imagine that you're watching a short video of a pendulum swinging from side to side. If someone plays the video backward, you may not notice. The motion still looks sensible. The pendulum moves left, then right, then left again. Nothing gives away which version came first. Now imagine a video of a glass slipping from a table and shattering on the floor. Play that backward and the trick is immediately clear. Pieces of glass jump together, rise from the ground, and settle neatly on the table. No one needs to be told that the film is reversed. Your mind knows at once that something is wrong. Why? The basic laws used to describe motion do not always care about the difference between forward and backward. A planet moving around a star can often be described just as well if its motion is reversed. Two small particles colliding can look perfectly reasonable in either direction. At that level, nature does not seem to place a large sign over one direction saying forward and another saying backward. Yet our lives are full of signs. Ice melts in a warm room. Coffee cools on a desk, smoke spreads through the air. Rooms become untidy with remarkable efficiency. Hair turns grey. Fruit ripens, softens, and eventually becomes something you would rather not find at the back of the cupboard. We never see these processes reverse on their own. The cooled coffee does not suddenly pull warmth out of the room and become hot again. The smoke does not gather itself from every corner and return to the candle. The forgotten banana does not recover its youth and become firm, green, and optimistic. Somewhere between the rules that describe tiny pieces of matter and the ordinary world we experience, a direction appears. That direction is often called the arrow of time. It is not a physical arrow floating through space. It is a way of describing the fact that many events happen in a clear order and not the other way around. We can tell the difference between earlier and later because the universe leaves evidence behind. Broken glass tells us there was once a whole glass. Ash tells us there was once a fire. A footprint tells us someone stepped there. A memory tells us something happened to us before this moment. The question is not only why time passes, it is why passing time seems to point one way. Before we go further, where are you listening from tonight? And what time is it in your part of the world? Perhaps it is late and the room is quiet. Perhaps it is early morning, and you are pretending that being awake was entirely your own decision. Maybe you are listening in the middle of the afternoon, which is also a perfectly respectable time to think about the foundations of reality, especially if there is tea nearby. There is something fitting about people in different places hearing the same question at different local times. Your clock may show 1 hour while another listener sees a completely different number. Relativity tells us that time itself can pass at slightly different rates, depending on motion and gravity. But even with those differences, everyone still experiences events in the same broad order. We are born before we grow older. We hear a question before we answer it. We press play before the video begins. If you enjoy calm journeys through science, and if this kind of gentle investigation helps you relax, you can like the video and subscribe to the channel. It helps more people find this quiet corner of physics. There is no need to do it immediately, of course. We are discussing time, so delaying a small task is almost a practical demonstration. Now settle in and let us begin with the thing that makes this problem so easy to miss. Human life is built around direction. We make plans for the future and keep records of the past. We apologize for things we have done, not things we're going to do. We prepare for tomorrow using lessons from yesterday. Language itself is arranged around this difference. We say an event has happened, is happening, or will happen. Our thoughts place us inside a moving sequence. Because this arrangement is so natural, it can feel as though the direction of time must be one of the most basic rules in the universe. It seems reasonable to imagine that every clock is measuring some deep forward movement built into reality. Seconds arrive one after another. The present replaces the past. The future waits its turn. The trouble is that many fundamental descriptions of nature do not contain this everyday sense of movement. Suppose two smooth balls roll toward each other on a perfectly level surface, collide, and roll apart. If friction is absent and the collision is simple, a backward recording also looks physically possible. The balls roll together, collide, and return along their original paths. The same rules describe both versions. This is known as time reversal symmetry. The name sounds technical, but the idea is straightforward. If a process remains allowed when its order is reversed, then the law describing it does not choose a preferred direction. Many important laws have this property, at least in the situations where they are normally used. They tell us how one state can lead to another, but they do not always say which state must come first. The mathematics may connect moments without announcing which one belongs to the past. That is strange because our experience is not symmetrical at all. You can stir milk into coffee until the two are mixed. You cannot normally stir the same cup in the opposite direction and separate the milk again. The exact motions of the molecules are governed by laws that allow reversal, yet the whole drink behaves in a one-way fashion. Once mixed, it stays mixed. The same is true of perfume released in a room. At first, the scent is concentrated near the bottle. Soon, moving air and countless molecular collisions spread it around. A person entering later may smell it from across the room. The molecules do not lose their ability to move in reverse. Nothing in their individual motion makes a return impossible, but they do not all gather back into the bottle together. Why not? The answer has less to do with what is forbidden and more to do with what is overwhelmingly unlikely. There are many more ways for perfume molecules to be spread through a room than there are ways for every molecule to remain crowded near the open bottle. There are many more arrangements of milk and coffee in which they are mixed than arrangements in which they are neatly separated. There are many more ways for the pieces of a glass to lie scattered across a floor than ways for them to form one complete drinking glass. When a system changes naturally, it tends to move from an unusual arrangement toward a more common one. That tendency gives the ordinary world its direction. Physicists describe this using entropy. Entropy is often introduced as disorder, although that word can be misleading if taken too literally. A tidy bedroom and an untidy bedroom may feel like a useful example, especially to anyone currently ignoring a chair covered in clothes. But entropy is more precise than household neatness. It concerns the number of microscopic arrangements that can produce the same overall condition. Think of a new pack of playing cards arranged by suit and number. That exact order is very special. There are extremely few arrangements that look perfectly organized in that particular way. Shuffle the cards and you can produce an enormous number of mixed arrangements. Most possible arrangements look random. If you continue shuffling, you expect to move among those mixed states. You do not expect the deck to return by accident to its original order. It could happen. The laws of motion do not ban it. But the odds are so small that waiting for it would require more patience than even a sleep science channel can reasonably request. This is where the direction of time begins to emerge. The future is the direction in which entropy tends to increase. The past is the direction in which entropy was lower. That statement may sound as if it explains everything at once, but it creates another question. If natural systems move toward more probable arrangements, how did the universe begin in such an improbable condition? To have an arrow of time today, there must have been a difference between the past and the future. The early universe must have had the kind of order that could gradually change into the more complex and spread out conditions we see now. Without that special beginning, there would be no clear direction for entropy to increase. This makes the origin of time's direction partly a question about the origin of the universe. The early universe was extremely hot and dense, but it was also remarkably smooth on very large scales. Matter was distributed with great uniformity. That smoothness may sound like disorder, because everything was mixed together, but gravity changes the story. In a universe controlled by gravity, smooth matter can represent a low-entropy condition. Gravity causes matter to gather into clumps. Those clumps become stars, galaxies, planets, and eventually places where people lose matching socks. As structures form, stars shine and release energy. Heat flows from warmer regions to cooler ones. Matter changes, radiation spreads, black holes appear. The range of possible arrangements grows, and entropy rises. The universe did not begin as a collection of finished objects scattered randomly through space. It began in a condition that allowed enormous change. The direction of time may come from that initial condition, and from the way physical systems develop from it. So the arrow is not necessarily an extra force pushing events forward. It may be the result of where the universe started. This distinction matters. We often imagine time as a current carrying everything along, but physics may not need a current. It may need only a sequence of changing states and a boundary condition at the beginning. The direction we call forward could be the direction away from the universe's unusually ordered past. That helps explain broken glasses and cooling drinks, but it also reaches into memory, cause and effect, and life itself. A memory is a physical record. When your brain stores an experience, cells change. Connections between neurons are strengthened or weakened. Energy is used, heat is released. The process leaves a trace in the present that corresponds to an earlier event. You remember the past because the past has left physical evidence. The future has not left those traces. There is no memory of tomorrow stored in your brain because the events of tomorrow have not produced changes in it. The psychological direction of time, the feeling that we know the past and face an uncertain future, is tied to the same physical processes that increase entropy. This is also why records point backward. A photograph exists because light from an earlier scene reached a camera. A fossil exists because an organism affected material around it. A crater exists because an impact took place. Present objects contain information about previous conditions. We do not find reliable records created by events that have not happened. Cause and effect follow a similar pattern. A match is struck, then the flame appears. A stone hits water, then ripples spread. A doorbell rings, then someone wonders whether pretending not to be home is morally acceptable. Energy moves, information spreads, and the world changes in ways that leave consequences. Could the laws be written in a way that runs backward? In many cases, yes. Could the ripples gather from the edge of a pond, converge at one point and throw a stone into your hand? The motion is not forbidden in the simplest description. It is simply so fantastically unlikely that we never expect to see it. Our sense of causality grows inside a universe where low entropy conditions lie behind us and higher entropy conditions lie ahead. Even living things depend on this direction. A body takes in concentrated energy from food and releases more spread out energy as heat. Plants receive energy from sunlight and use it to build organized structures. Animals eat plants or other animals and maintain complex bodies for a limited time. Life creates local order, but it does so while increasing entropy in the wider environment. This does not violate the overall tendency. A refrigerator can make its interior colder, but it releases more heat into the room. A person can organize a desk, but the work requires energy and usually produces other forms of disorder, including the temporary mystery of where the stapler went. Life is possible because energy flows. Energy arrives in useful forms, passes through biological systems, and leaves in less concentrated forms. The arrow of time is present in every breath, every meal, every heartbeat, and every attempt to stay awake through a meeting scheduled too early. A creature that remembers, learns, and predicts needs this difference between past and future. It uses stored information from earlier events to make decisions about later ones. Evolution itself depends on sequences that build on what came before. Organisms reproduce, variations occur, environments select, and populations change across generations. None of this means we fully understand why time has a direction. Entropy gives us the most successful explanation for the arrow we observe, but the deepest part of the puzzle remains open. Why did the universe begin in a low-entropy state? Was that beginning necessary, accidental, or part of a larger structure we do not yet understand? Does the arrow of time exist everywhere in the same way? Could there be regions or conditions where it points differently? Is the flow we feel a fundamental feature of reality, or a result of how memory and information work? These are not questions asked only for philosophical entertainment. They sit at the meeting point of thermodynamics, cosmology, quantum theory, and the study of information. A clear answer would affect how we understand the beginning of the universe and the nature of physical law. It may also change how we think about the present. The present feels special because it is where records of the past meet uncertainty about the future. Behind us lies a trail of evidence. Ahead of us lies a range of possibilities. We stand at the boundary, updating memories and making predictions. Physics does not yet agree on whether that boundary is a basic part of the universe or a feature of conscious experience. Some descriptions treat all moments as equally real. In that view, the difference between past and future does not come from time flowing. It comes from the arrangement of events within space-time and the increase of entropy along one direction. Other approaches suggest that time may emerge from change, correlations, or the growth of information. Instead of being a stage on which events happen, time might be a way of describing relationships between events. For now, it is enough to notice that the direction of time is not as simple as a clock hand moving around a face. Clocks measure regular change. They compare one process with another. A pendulum swings. A crystal vibrates. Atoms shift between energy states. None of these devices explains why shattered glass stays shattered or why memories point backward. The answer begins with statistics, probability, and the history of the universe. A single molecule does not know which way time is going. A small collision does not carry a label saying past on one side and future on the other. Direction becomes clear when enormous numbers of particles interact, and when we compare more ordered conditions with more probable ones. That is why the arrow of time can feel both universal and hidden. It governs almost every ordinary process, yet it may not appear in the simplest microscopic rules. To understand it properly, we need to look more closely at what physicists mean by an arrow, why several different arrows seem to point together, and what would happen if even one of them pointed the other way. That is where our next step begins, with the quiet difference between a universe that can be described backward and a life that can only be lived forward. A universe that never rewinds sounds like a simple description of ordinary life. We see events happen, we watch their consequences spread, and we move on. No one expects spilled water to rise from the floor, gather into a glass, and place itself back on the table. No one waits for smoke to return to a candle, or for yesterday's dinner to reassemble itself in the kitchen. The direction seems so dependable that we rarely notice how strange it is. The phrase arrow of time was introduced to describe this one-way order. It gives a name to the difference between earlier and later, not by referring to clocks, but by looking at what physical events actually do. A clock can tick forward because we built it that way. The deeper question is why the rest of nature appears to agree. Consider a quiet room with a single ball rolling across the floor. If the surface were perfectly smooth and there were no friction, the ball could continue at a steady speed. A recording of that motion would not reveal whether it was being played forward or backward. The ball would simply move in the opposite direction. Both versions would look reasonable. Now place a second ball in its path. The two collide and move apart. Reverse the recording, and the balls come together, collide, and return along their original routes. Nothing about the reversed motion looks impossible. The same physical rules can describe it. This is one of the central puzzles. The basic laws governing many small-scale events often work in either time direction. They connect one state to another without insisting that one must be called the past. Yet large-scale events usually show an obvious order. A glass can become fragments, but fragments do not become a glass. A warm drink can cool, but a cool drink does not draw scattered heat from the room and warm itself. A person can grow older, but the process does not reverse after a good night's sleep, however hopeful the advertising may be. The arrow of time appears most clearly when many particles are involved. A single atom moving through empty space does not look old or young. It does not carry a tiny calendar. A pair of particles can collide in a way that remains sensible when viewed backward. But place an enormous number of particles together, and their collective behaviour develops a strong preference. This preference is not usually a new force. There is no known push that moves every object toward the future. Gravity pulls masses together. Electric forces attract or repel charged particles. The arrow of time works differently. It comes from the way possible arrangements are distributed, and from the condition in which a system begins. Imagine a box divided into two halves by a removable wall. Gas fills the left half while the right half is empty. Remove the wall and the gas spreads through the entire box. The molecules bounce in every direction, colliding with one another and with the walls. Nothing tells an individual molecule that it must move right. Some move left, some move right, and some change direction repeatedly. Taken together, however, the gas fills the available space. If you wait, the molecules will continue moving. In principle, they could all return to the left half at the same time. No basic rule forbids it. The difficulty is probability. There are vastly more ways for the gas to be spread throughout the box than there are ways for every molecule to be gathered on one side. The spread-out condition is not preferred because the molecules have a plan. It is preferred because almost every possible arrangement looks like that. The concentrated condition is rare. Once the wall is removed, the system leaves a special arrangement and moves toward one that can be produced in far more ways. This difference creates a practical direction. We identify the concentrated gases earlier and the spread-out gases later. If we saw a film in which gas gathered itself into one half of a box, we would assume the film had been reversed. The same reasoning applies to many familiar events. When a drop of ink enters water, the ink begins in a concentrated region. Molecular motion gradually spreads it through the glass. There are countless mixed arrangements and very few unmixed ones. Once the ink is evenly distributed, random motion continues, but the water remains mixed because mixed states dominate the possibilities. A reversed film would show pale water slowly pushing colour into a shrinking cloud until one perfect drop forms. The motion of each molecule could still follow valid rules, but the coordination required would be extraordinary. Every collision would need to occur in just the right way. The chance is so small that it has no practical role in everyday life. That phrase, no practical role, matters. Physics sometimes distinguishes between impossible events and events that are merely unlikely. A stone floating upward without any force would conflict with the ordinary description of gravity. A box of gas gathering itself into one corner does not necessarily conflict with microscopic motion. It is simply so improbable that the difference becomes nearly meaningless for any realistic observation. The arrow of time is therefore tied to statistics. It becomes reliable because large systems contain enormous numbers of particles. Small uncertainties average out. Rare reversals become less likely than winning every lottery you can imagine while being struck by several carefully scheduled bolts of lightning. Even so, the arrow is not only about gas and ink. Physicists speak of several arrows because different features of reality so all distinguish past from future. There is a thermodynamic arrow. This is the direction in which energy becomes more spread out, and in which systems move toward more probable arrangements. Cooling, mixing, friction, decay, and the ordinary production of the waste heat all belong to this direction, there is a psychological arrow. We remember the past and not the future. Our minds contain records of earlier events. A smell can bring back a childhood kitchen. A song can recall a journey. A small scar can remind us of a decision that seemed sensible at the time. These records point backward. There is a causal arrow. Causes come before their effects. A hand pushes a cup, the cup falls, and the floor becomes more complicated. We do not see the broken pieces jump upward and then cause the hand to move. There is also a radiation arrow. Waves move outward from their sources. Drop a stone into a pond and ripples travel away from the point of impact. Turn on a lamp and light spreads into the room. Radio signals leave an antenna and move through space. The reverse pattern, waves arriving from every direction and concentrating perfectly at one point, is allowed in some descriptions but is not what we normally observe. Cosmology introduces another possible arrow. The universe is expanding. On large scales, distant galaxies are moving farther apart as space itself changes. The past contained a hotter and denser cosmos, while the future appears to lead toward a colder and more spread out one. This expansion provides a large-scale difference between earlier and later. The interesting fact is that these arrows point the same way. The direction in which energy spreads is also the direction in which we form memories, observe effects after causes, watch waves travel outward, and see the universe expand. Why should they agree? One possibility is that they all depend on the same low-entropy past. If the universe began in a very special condition, then every process developing from that condition would inherit a shared direction. Memory formation, radiation, biological activity, and ordinary cause and effect would all follow the route from a less probable state toward more probable states. This does not mean every local event becomes more disordered at every moment. A seed grows into a plant. A builder turns bricks into a house. A cook turns ingredients into a meal, sometimes even intentionally. Local order can increase. The wider process still produces a net increase. The plant uses sunlight and releases heat. The builder consumes energy, creates waste, and changes the environment. The cook uses fuel, warms the kitchen, and produces dishes that remain in the sink with a surprising confidence in their long-term residency. Order can be created in one place by increasing the spread of energy elsewhere. The arrow does not forbid structure. It helps make structure possible by providing energy flows that living and non-living systems can use. A waterfall offers a simple example. Water high above the ground has stored energy because of its position. As it falls, that energy becomes motion, sound, turbulence, and heat. A water wheel can capture part of the flow and perform useful work. The wheel turns because there is a difference between the higher water and the lower water. Once the water reaches the bottom and its energy is widely distributed, the opportunity is reduced. To repeat the process, sunlight must help lift water through evaporation, clouds, and rain. The larger system includes a constant flow of energy from the sun into space. Our own lives depend on similar differences. Food contains energy and forms our bodies can use. We break down molecules, maintain temperature, repair tissue, move muscles, and support brain activity. The energy eventually leaves us in less useful forms, mostly as heat. A body stays organized not by escaping the arrow of time, but by working within it. Life is not a pause in physical decay. It is an active process that uses energy to delay some changes while causing others. This gives the arrow a close connection to irreversibility. An irreversible process is one that does not naturally return to its starting condition. Friction is a common example. Rub your hands together and motion becomes heat. The warmth spreads into your skin and the surrounding air. It does not gather itself later and force your hands to slide apart in the exact reverse motion. The underlying particles still obey rules that may be reversible. The irreversibility appears because the energy has been shared among too many microscopic motions. Recovering the original movement would require every particle to coordinate with impossible precision. A similar thing happens when a ball bounces on the floor. Each bounce is lower than the last because some organized motion becomes sound, heat, and deformation. The energy is not destroyed, it is distributed. The floor vibrates, air moves, the ball warms slightly, the room gains a tiny amount of heat. To reverse the process, all those scattered motions would need to return at the right moment. Sound waves would gather, heat would focus, the floor and air would push the ball upward. Nothing in the simplest microscopic picture makes this absolutely forbidden, but nature does not arrange the required cooperation. This is why the arrow is easy to see in large objects. A large object is connected to its environment. It exchanges heat, produces sound, leaves marks, and becomes linked with surrounding matter. Information about its motion spreads outward. Once information has spread into the environment, reversing the event becomes difficult beyond practical possibility. The world has recorded what happened. A shattered glass does not only become pieces, it sends vibrations through the floor, moves air, produces sound, scatters light, and changes the positions of countless particles. A complete reversal would need to recover all of those details. The room itself would have to participate. That is one reason a reversed film looks strange. The camera may show the glass reassembling, but the true physical reversal would involve much more than the visible fragments. Every air current, sound wave, vibration and heat transfer would need to reverse as well. The event is connected to the rest of the universe. At the human scale, this connection makes the past stable. Evidence accumulates. One event leaves many records, and those records spread. Suppose someone walks across wet ground. Their steps leave footprints. Light reflects from the scene. Air is disturbed. Mud sticks to their shoes. Perhaps a camera records them. Perhaps another person notices. The event produces multiple traces. Those traces allow us to infer what happened. We reconstruct the past because the past leaves records in the present. The future does not provide the same kind of evidence. We can predict future events, sometimes very well. We know when an eclipse will occur. We know that an unsupported object will fall. We can estimate tomorrow's sunrise. But predictions are not memories. They are conclusions based on present conditions and physical laws. They can fail if our information is incomplete. The past feels fixed because it has already produced consequences. The future feels open because many possible consequences remain compatible with the present. Some interpretations of physics question whether the future is truly open. In a fully deterministic description, the state of the universe at one moment would determine every other moment. The future would be fixed even if no one could calculate it. Other theories give probability a more fundamental role. Quantum mechanics does not always assign one definite outcome before a measurement. It describes a range of possible results and their likelihoods. Both views still face the arrow of time. A deterministic universe can contain irreversible large-scale behavior. A probabilistic universe can also produce a stable direction. The question is not simply whether the future is predictable. It is why records, heat flow, and probability all distinguish one temporal orientation. One tempting idea is that the arrow comes from consciousness. Perhaps time seems to move forward because minds process information in sequence. Without observers, there might be no experienced flow. Consciousness certainly shapes how time feels. Boredom stretches minutes. Absorption makes hours disappear. Fear can make a brief event feel longer in memory. Sleep removes long intervals from awareness. Yet the physical arrow does not depend on someone watching. Stars burn, rocks erode, and radioactive materials decay in places no observer visits. The universe was changing long before nervous systems existed. Our experience of direction may be built on top of a physical difference. Brains form memories by changing their own structure. Those changes consume energy and produce heat. The psychological arrow points with the thermodynamic arrow because remembering is a physical process. There is a useful thought experiment involving a creature whose memories point in the opposite direction. Imagine a being that remembers what we call the future, but knows nothing of what we call the past. From its perspective, broken objects might appear to assemble, smoke might gather into wood, and adults might become children. Could such a creature exist? The idea is difficult because memory itself requires records. To remember an event, the creature's brain must contain a physical trace caused by that event. If the trace exists before the event in our time direction, then ordinary causality becomes confused. The creature would need a universe with starting conditions arranged in the opposite way. In a region where entropy decreased toward what we call the future, inhabitants might define their own future in the direction of increasing entropy. Their language would reverse our labels, but their experienced arrow would still point from lower entropy toward higher entropy. This suggests that conscious observers naturally align themselves with the thermodynamic direction available to them. They remember the side with more records and anticipate the side with fewer. The arrow of time may therefore be less like a signpost placed on the universe and more like a difference that makes change possible. Water flows downhill because there is a height difference. Heat flows from hot objects to cold ones because there is a temperature difference. Physical processes develop because useful differences exist. Time's direction could arise because the universe began far from equilibrium. Equilibrium is the condition in which large-scale differences have mostly disappeared. Temperatures even out. Energy becomes spread. Useful contrasts fade. A universe already in complete equilibrium would be very different from ours. There would be no stars shining into colder space, no warm planets, no chemical differences for life to exploit, and few processes capable of making durable records. Change might still occur at microscopic scales, but there would be little organized history. Our universe contains strong differences. Stars are hot while space is cold. Matter is gathered into galaxies while vast regions remain nearly empty. Planets have complex chemical environments. These differences allow events to happen and leave traces. Every burning star, living cell, weather system, and working engine uses a departure from equilibrium. As those systems operate, they reduce some differences and create new forms of spread. The arrow points through that activity. The statement that the universe never rewinds is therefore not an absolute claim that reversed motion is forbidden. It means that complete large-scale reversal is not observed because the conditions required are too precise and too improbable. Small reversals can occur. Molecules in a liquid constantly move in ways that briefly oppose the overall trend. Tiny fluctuations can make a small region slightly more ordered for a short time. At very small scales, researchers can observe temporary changes that resemble a local decrease in entropy. These fluctuations do not overturn the arrow. They show that the arrow is statistical. For a few particles over a brief interval, unusual behavior is possible. As the number of particles and the length of time increase, the overall trend becomes increasingly reliable. A coin tossed a few times may produce several heads in a row. Toss it millions of times, and the result approaches an even balance. Large numbers make statistical patterns stable. In the same way, a small collection of particles can briefly behave unexpectedly. A room full of air will not suddenly rush into one corner and leave everyone else discovering how long they can hold their breath. The reliability of the arrow grows from scale. It is weak and flexible in tiny systems, then firm in the world of tables, oceans, planets, and people. This scale difference explains why the laws can look reversible underneath, while experience remains irreversible above. There is no contradiction. The two descriptions focus on different levels. Microscopic laws track exact motions. Large-scale laws track overall conditions such as temperature, pressure, and energy distribution. When we move from one level to the other, we stop following every particle. We use averages and probabilities. That loss of detail is not merely a limitation of our instruments. Large-scale descriptions are useful precisely because the exact microscopic information is overwhelming. To describe a cup of tea, we do not list the position and speed of every molecule. We state its temperature, volume, and composition. Once we describe the system in this broader way, Many different microscopic arrangements count as the same visible state. The number of those arrangements becomes central, and the arrow appears naturally. The next question is therefore not whether disorder simply grows, or why bedrooms resist cleaning. It is what entropy actually measures, why it increases so reliably, and why a concept based on unseen arrangements can control the direction of every ordinary process around us. To understand why entropy controls so much of what happens around us, it helps to begin with a simple correction. Entropy does not mean that everything must become messy in the everyday sense. A tidy room can become untidy, but a pile of laundry is not a scientific measuring device. Entropy describes how many different microscopic arrangements can produce the same overall condition. That distinction matters because the world we see is built from particles we cannot track individually. A cup of tea contains an enormous number of water molecules, along with molecules from the tea, milk, sugar, and anything else added during a moment of optimism. Every one of those particles is moving, colliding, rotating, and exchanging energy. Their exact positions change constantly. When we look at the cup, we do not see those details. We see one object with a certain temperature, colour, volume, and taste. Many different arrangements of the molecules would give us the same visible cup of tea. The number of possible hidden arrangements is related to its entropy. Imagine a box containing a small number of coloured beads, half a blue and half a white. Place all the blue beads on the left side and all the white beads on the right. That arrangement looks ordered because the colours are separated. Shake the box and the beads mix. There are many ways for the mix pattern to appear. One blue bead might sit beside 3 white beads. Another might rest in a corner. A different shake produces a different pattern, but from a distance they all look mixed. There are far fewer arrangements in which every blue bead is on one side and every white bead is on the other. The separated condition is special. The mixed condition is common. Entropy is higher in the mixed condition, because there are more microscopic arrangements that count as the same general state. This is why mixing happens so easily. This system is not trying to become untidy. It is simply moving through possible arrangements, and almost all of them look mixed. If the box contained only 4 beads, you might occasionally shake it and recover the separated arrangement by accident. With a small number of objects, unlikely events can still occur. If the box contained millions of beads, an accidental return to perfect separation would be effectively impossible. The number of mixed arrangements would be so much larger that the ordered state would almost never appear. The same logic applies to gases, liquids, heat, and most of the processes that show a clear direction in time. A gas spreads through a room because there are more ways for its molecules to be distributed than concentrated. Heat flows from a warm object into a cooler environment because there are more ways for the energy to be shared than confined. A drop of ink spreads through water because mixed arrangements greatly outnumber separated ones. The increase of entropy is not a command given to each particle. No molecule receives instructions. Every particle follows ordinary physical rules, while the large group moves toward the conditions that can be produced in the greatest number of ways. This is often expressed through the second law of thermodynamics. In an isolated system, entropy tends to increase. The word tends is important. The second law is statistical. It describes what is overwhelmingly likely to happen when very large numbers of particles interact. It does not say that a small decrease in entropy can never occur. Tiny systems can fluctuate. A few particles may briefly gather into a more ordered arrangement. Energy may move in an unusual direction for a short time. For large systems, those fluctuations become less significant. A cup of cool tea will not suddenly become hot by drawing scattered warmth from the room. The event is not absolutely forbidden at the microscopic level, but it would require an unbelievable coordination of particles. Every molecule in the surrounding air would have to move in just the right way. Collisions would need to direct energy into the cup rather than away from it. The tea would warm while the room cooled by exactly the corresponding amount. There are so many more ways for heat to remain spread out that the reverse event has no realistic chance of occurring. This explains why entropy is connected to probability rather than simple disorder. Consider a deck of cards. Arrange it in a particular order, perhaps by suit and number. That exact sequence is one possibility among an enormous number of possible sequences. Shuffle the cards once and the original order is probably lost. Shuffle again and you obtain another arrangement. Almost every possible sequence looks random to us, while only a few look deliberately organised. The cards do not prefer randomness. There are simply more random-looking sequences available. If you keep shuffling, returning to the original order is possible. It is also so unlikely that you should not organise your afternoon around it. Physical systems behave in a similar way, except they involve far more components than a deck of cards. A glass of water contains more molecules than anyone could count individually. A room contains vast numbers of air molecules. A human body contains an even more complicated collection of particles, chemical reactions and energy transfers. When those systems change, they move through possible microscopic arrangements. High entropy states dominate because there are more of them. This does not mean that high entropy always looks chaotic. Sometimes a high entropy state appears smooth and uniform. A gas spread evenly through a box looks calm. Milk mixed into coffee looks uniform. A room at one temperature may appear perfectly still. These conditions have high entropy because the particles and energy are widely distributed. There are many microscopic ways to create the same smooth appearance. A low entropy state may look more visibly structured. Gas confined to one side of a container has a strong difference between the occupied and empty regions. A hot object in a cold room has a clear temperature difference. A battery stores chemical energy in a form that can later perform useful work. Low entropy often involves usable differences. High entropy often means those differences have been reduced. This connection helps explain why entropy matters for machines. An engine works because there is a difference between hot and cold. Heat flows from the hotter region toward the cooler one, and part of that flow can be used to produce motion. Once everything reaches the same temperature, the engine can no longer extract useful work from the heat. The energy still exists, but it has become too evenly spread. A battery works because its internal chemicals are arranged in a condition that can drive an electric current. As the battery is used, the chemicals move toward a more stable arrangement. The stored difference decreases, and eventually the battery can no longer power the device. Charging the battery restores that useful difference, but doing so requires energy from somewhere else. The charger draws electricity. Power stations release heat. The wider environment experiences an increase in entropy. Local decreases are possible because the total process still moves in the usual direction. A refrigerator is a familiar example. Inside, it creates and maintains a cooler region. That may appear to oppose the natural flow of heat. The refrigerator does not reverse the second law. It uses electrical energy to move heat from the colder interior into the warmer room. The coils at the back become hot. The motor produces additional heat. The total entropy of the refrigerator and its surroundings increases. This is why leaving the refrigerator door open does not cool the kitchen. It moves heat around while adding more from the motor. The machine eventually warms the room, though it may also provide a useful light for anyone standing there at midnight wondering whether cheese counts as a complete meal. Living organisms also create and maintain local order. A plant grows from a seed. A child develops into an adult. Cells repair damage. Bodies maintain temperature and organize complex chemical processes. These changes do not violate entropy because living things are not isolated systems. They take in energy and matter, transform them, and release waste and heat. A plant receives concentrated energy from sunlight. It uses part of that energy to build sugars, tissue, roots, and leaves. It releases heat into the environment. An animal eats food containing stored chemical energy. The body uses that energy to move, think, grow, repair itself, and maintain internal conditions. The energy eventually spreads into the environment. mostly as heat. A living body can preserve its internal organisation only by increasing entropy outside itself. When the supply of usable energy stops, the body loses the ability to maintain its highly organised state. Chemical differences fade, temperatures equalise, structures break down, life does not escape the direction of time. It depends on the flow that creates that direction. The sun plays a major role in this process on Earth. It sends concentrated energy toward our planet in the form of sunlight. Earth absorbs that energy and later releases it into space in a more spread out form. Between those two stages, sunlight drives weather, ocean currents, plant growth, and almost every food chain. It powers many of the differences that make complex activity possible. The energy arriving from the sun is useful because it comes from a hot source. Earth sends energy away toward the much colder background of space. That temperature difference allows work to happen. Entropy increases throughout the larger process, while local structures such as storms, forests, animals, cities, and regrettably complicated filing systems can form. This may seem surprising because we often associate increasing entropy with the destruction of structure. Yet entropy and structure can grow together when energy flows through a system. A hurricane is highly organised. It has a clear shape, strong winds, and a rotating pattern. It forms because warm ocean water transfers energy into the atmosphere. The storm helps move heat and moisture, increasing entropy in the wider environment. A flame also has structure. It maintains a recognisable shape and produces light. It exists while fuel reacts with oxygen and releases energy. Once the fuel is used, the flame disappears and the products remain in a more stable state. Order can arise temporarily as a system moves energy from one place to another. This is important for understanding why the universe became more complex even while entropy increased. The early universe was much smoother than the universe we see today. Matter was distributed with remarkable uniformity. Later, gravity pulled matter together. Gas formed stars. Stars gathered into galaxies. Planets formed around some of those stars. At first glance, this looks like a move from disorder to order. Smooth matter became organised structures. Gravity changes the meaning of the situation. For systems controlled by gravity, a smooth distribution of matter can represent a low-entropy state. Clumping creates new possibilities. As matter falls together, it gains speed and heats up. Stars form and release radiation. Massive stars explode and scatter heavier elements through space. Black holes appear and contribute enormous entropy. The universe can become more structured in visible ways while its total entropy increases. This is one reason household examples have limits. Entropy is not simply a scientific word for mess. Gravity, energy, and the number of microscopic arrangements must all be considered. A neat stack of papers may become scattered, but physics is not judging your desk. It is counting possibilities. The same principle explains why some processes are reversible in theory, but irreversible in practice. Imagine filming 2 billiard balls colliding on a smooth table. Reverse the film and the motion remains believable because only a few objects are involved and little energy is lost. Now film a billiard ball rolling across a rough carpet until it stops. The ball's organised motion becomes microscopic motion in the carpet, the ball, and the surrounding air. Some energy becomes sound, some becomes heat. A reversed film would show the stationary ball beginning to move as the carpet cools slightly and scattered vibrations gather into a coordinated push. The total energy could still be conserved, but the required arrangement is extraordinarily unlikely. The process looks irreversible because the energy has spread among too many hidden degrees of freedom. The phrase degrees of freedom refers to the different ways parts of a system can move or store energy. A molecule may move through space, rotate, vibrate, and interact with nearby particles. A solid contains atoms that vibrate. Air carries pressure waves, surfaces bend slightly when struck. When a large object loses visible motion, the energy has not vanished. It has entered these less visible forms. Recovering the original motion would require gathering that energy from every microscopic location and returning it in one coordinated event. This spreading of energy is why friction gives time a direction. It is also why real machines are never perfectly efficient. A machine converts energy from one form into another, but some always spreads into unwanted heat, sound, or deformation. Engineers can reduce these losses, but they cannot eliminate the overall thermodynamic cost. A car engine turns chemical energy into motion, yet much of the energy heats the engine, exhaust, road, and air. Brakes convert motion into heat. Tires deform. Sound spreads outward. The car moves because useful energy is being degraded into less useful forms. The fuel does not reassemble itself after the journey. The hot exhaust does not return to the engine and reconstruct the original chemicals. Entropy measures the loss of these concentrated differences, though the total energy remains. This distinction between energy and useful energy is essential. The universe does not run out of energy in the ordinary sense. Energy changes form and is conserved. What decreases is the amount of energy available to perform organized work. A warm room contains a great deal of thermal energy. If every part of it has the same temperature, there is no temperature difference to run an engine. The energy is present, but it cannot easily be directed. A hot cup in a cold room can produce a flow of heat. Once the cup and room reach the same temperature, the opportunity disappears. Entropy increases as usable differences fade. This gives the second law a close relationship with time. Earlier states often contain stronger differences. Later states contain more evenly distributed energy. A block of ice in warm water represents a clear temperature difference. As the ice melts and the water settles at one temperature, the difference is reduced. A stretched spring stores mechanical energy. Release it and the spring moves, producing vibration, sound, and heat. Eventually it stops. The energy has spread. A compressed gas can push a piston. Once the pressure equalizes, it can no longer perform the same work without outside intervention. In each case, the initial condition is special. The final condition can be produced in many more microscopic ways. This is why the second law depends on the system having started away from equilibrium. If a system begins in equilibrium, there is no obvious overall direction for it to move. Its large-scale properties remain stable even while its particles continue moving. A sealed box of gas at one temperature and pressure is close to equilibrium. Molecules still collide constantly, but there is no large-scale flow of heat or matter. The system has already reached one of its most probable conditions. Time does not stop inside the box. Microscopic motion continues. What disappears is the visible arrow created by change toward equilibrium. This suggests that the arrow of time is strongest where differences remain. Our universe contains many systems far from equilibrium. Stars are much hotter than surrounding space. Planets contain temperature differences, chemical differences, and moving fluids. Living organisms maintain complex internal conditions. These systems create visible histories because they can change. A star burns through fuel, a mountain erodes, a river carries sediment, a body ages. Each process consumes or redistributes a difference. The evidence left behind points toward the direction in which entropy has increased. Ash tells us that fuel burned. A dry riverbed tells us that water once flowed. Weathered rock tells us that wind, water, or ice acted over time. A cooled object tells us it was once warmer than its surroundings. We infer the past from present conditions because irreversible processes leave records. There is a further complication. Entropy depends partly on how we describe a system. If we knew the exact position and motion of every particle, the microscopic description might preserve information in a way that the large-scale description does not. When we speak of entropy increasing, we often group many detailed states into the same general category. We call all evenly mixed cups of tea one type of condition, even though their molecules are arranged differently. We ignore details that are too small or numerous to track. Some physicists have asked whether irreversibility comes from this loss of information. Perhaps the fundamental laws preserve every detail, while entropy rises because observers use simplified descriptions. That idea explains part of the story, but not all of it. Even an observer with excellent information would still find the low entropy past unusual. The universe appears to have started in a highly special state. Our limited descriptions do not explain why that state existed. The direction of time, therefore, involves both probability and history. Probability tells us why systems move from rare arrangements toward common ones. History tells us why they began in rare arrangements at all. If the universe had always been in equilibrium, there would be no long-lasting direction for entropy to increase. The fact that we observe an arrow means the past was different from the present. This is sometimes called the past hypothesis. It is the proposal that the early universe had very low entropy. The name makes it sound like a modest technical assumption, but it carries enormous importance. It provides the starting condition from which every familiar irreversible process can develop. The low entropy past allows stars to shine, heat to flow, records to form, and life to use energy. It gives physical systems room to change. Why the universe began that way remains one of the deepest questions in cosmology. The early universe was hot, but high temperature alone does not mean high entropy. The distribution of matter and the role of gravity must be included. Matter was smooth enough to allow gravity to create structures over time. That smoothness was highly special. It gave the universe a large capacity for future entropy growth. As stars and galaxies formed, energy was released and spread. As black holes formed, entropy increased dramatically. The universe moved away from its unusual beginning. Everything we call the future lies along that direction. The second law may therefore be less like a rule that pushes events and more like a description of how a special beginning develops. A broken glass does not need an extra force preventing it from reassembling. Its scattered condition is overwhelmingly more probable. A warm drink does not need a law forbidding it from heating itself. Energy naturally spreads among the many available arrangements. A body does not age because time carries it forward like a moving walkway. Maintaining biological order requires energy, and the processes involved cannot be perfectly reversed. This does not make aging simple. Biology adds repair, genetics, disease, environment, and many other factors. The thermodynamic direction provides the background within which those processes occur. Every repair mechanism has a cost. Every cell division uses energy. Every stored memory changes physical tissue. That last point leads to a more personal part of the arrow. Entropy explains why records form in one direction. A record is a physical object or state that has become correlated with an earlier event. A footprint is correlated with a footstep. A photograph is correlated with light that reached a camera. A scar is correlated with an injury. A memory is correlated with activity that changed the brain. Creating these records requires energy and increases entropy. A camera uses power. A nervous system processes signals. A mark is made by transferring force and altering material. Records accumulate toward the same direction as entropy. That is why the past appears full of information while the future appears uncertain. The present contains traces of what has already happened. We can study those traces, compare them, and build a history. We cannot inspect equivalent traces of events that have not yet occurred. Prediction uses current information to estimate what may happen. Memory uses current physical records to reconstruct what did happen. Both depend on the present, but they point in opposite directions because only one side has already left evidence. The next part of the puzzle lies inside that difference. The brain is made of matter and follows the same thermodynamic rules as everything else. Its memories are not separate from physics. They are physical changes created while energy is used and entropy rises. To understand why we remember yesterday but not tomorrow, we need to follow how an event leaves a trace, how the brain stores that trace, and why every act of remembering is aligned with the same direction as cooling tea, spreading gas, and a universe moving away from its unusually ordered beginning. Memory feels so natural that we rarely consider what a strange ability it is. You can sit in a quiet room, close your eyes, and return to a place that no longer exists in quite the same form. You can hear the voice of someone who is not present, picture a street you have not visited for years, or remember the exact moment you realised that a tray had just come out of the oven and should not be touched with an unprotected hand. The event is over, yet something remains. That remaining trace is what gives memory its connection to the direction of time. We remember events that have already changed us. We do not remember future events because they have not yet left physical traces in the brain. This may sound obvious, but it hides an important point. A memory is not a separate, weightless object stored somewhere outside physics. It is a physical condition inside a living system. Neurons have changed their activity. Connections between cells have been strengthened or weakened. Proteins have been produced. Chemical signals have moved. Energy has been used, and heat has been released into the surrounding tissue. Remembering yesterday is possible because yesterday helped shape the brain you have today. Tomorrow has not done that yet. The difference between past and future inside the mind therefore follows the same direction as the difference between a whole glass and its scattered pieces. One side has produced records, the other side has not. Suppose you walk along a beach and leave a line of footprints behind you. The prints contain information about where your feet touch the sand. Their shape may reveal the size of your shoes, the direction you were walking, and whether you were moving calmly or running away from a surprisingly confident seagull. The sand remembers your passage in a very simple sense. It has been changed by the event. The beach does not contain footprints from your walk tomorrow because that walk has not occurred. No pressure has been applied. No grains of sand have been moved. There is no physical mark to inspect. A human memory is far more complicated than a footprint, but the principle is similar. An experience affects the nervous system and leaves a pattern that can later influence thought and behaviour. Light reaches the eyes, sound reaches the ears, pressure, temperature, smell, taste, and signals from within the body enter the brain. Networks of neurons process those signals. Some of the activity fades almost immediately. Some last for seconds or minutes. A smaller portion creates changes that can remain for years. The brain does not record every detail with equal care. It selects, compresses, combines, and sometimes edits with the confidence of someone who has misplaced the original notes. This is why memory is not a perfect replay. It is a reconstruction. When you remember a conversation, you do not open a complete recording stored inside the skull. The brain rebuilds the experience using fragments. It may recover the general meaning, a facial expression, a particular sentence, or the feeling you had at the time. Missing details can be supplied by expectation, later knowledge, or imagination. The result can feel completely accurate even when parts of it have changed. That does not weaken the physical link between memory and the past. It shows that the link is practical rather than perfect. A memory is evidence that something affected the brain, but it may not preserve a flawless account of what happened. The same is true of other records. A footprint can be damaged by wind. A photograph captures only one angle. A written account may contain mistakes. A fossil preserves some structures while losing others. Records survive by carrying partial information from earlier conditions into later ones. To create a record, one system must interact with another. The event changes the recording system. Light changes material in a camera sensor. A stylus makes a groove in a surface. A moving object bends or breaks what it strikes. An experience changes neural activity. These changes are not free. They require physical processes, and those processes produce entropy. A camera uses electrical energy. A brain uses chemical energy supplied through the body. A mark in sand requires force. A computer storing information changes the state of physical components and releases heat. The formation of records is therefore aligned with the thermodynamic arrow. Records accumulate in the direction in which energy becomes more spread out. This gives us a useful way to understand the psychological arrow of time. The past is the direction containing causes of present records. The future is the direction in which new records will be formed. You know that you ate breakfast because your brain may contain a memory. The dishes may still be in the sink, and the amount of bread in the kitchen may have suffered a measurable decline. Several present conditions are connected to the earlier event. You do not know in the same way what you will eat tomorrow. You may have a plan. There may be food waiting in the refrigerator. You may make a confident prediction. None of that is a memory. A prediction is created from current information and assumptions. A memory is created from a physical interaction with an event that has already occurred. The difference is not simply a matter of grammar. It is built into the arrangement of evidence. Imagine finding a broken plate on the floor. You can infer that a whole plate existed earlier. The fragments fit together. Their edges match. The position of nearby objects may suggest how it fell. The sound may still be remembered by someone in the room. The present contains information about the plate's past. The same fragments do not normally reveal one unique future. They could be swept into a bin, repaired with glue, left on the floor for an unreasonable length of time, or carefully avoided by everyone who insists that somebody else will deal with them. Many future outcomes remain possible from the same present state. The past often seems more definite because present records restrict what could have happened. The future seems less definite because it has not yet produced the evidence that would select one outcome. This does not necessarily prove that the future is fundamentally open. A fully deterministic universe could still contain only one actual future. The problem is that observers inside the universe do not possess all the information needed to know it. The brain works with incomplete data. It builds models, estimates risks, and prepares possible actions. It uses memories of earlier events to reduce uncertainty about later ones. This is one of the main reasons memory evolved. A creature that can retain information about danger, food, shelter, and social relationships has an advantage. It can change its behavior based on what happened before. An animal that remembers where it found water can return. One that remembers the warning signs of a predator can respond more quickly. A person who remembers that a metal pan remains hot after leaving the oven may avoid repeating an educational but unpleasant experiment. Memory allows the past to guide action in the future. That arrangement depends on the arrow of time. Information is collected from events, stored through physical changes, and used later. The sequence runs from experience to record to decision. Reversing it would be difficult to describe. A brain would need to contain a reliable record before the event that created it. The person would remember touching the hot pan, then touch it, and only afterward lose the memory. A reversed film might show such a sequence, but the whole surrounding environment would also have to reverse. Heat would return from the air into the pan. Signals in the nervous system would retrace their paths. Chemical changes would undo themselves. Every scattered effect would need to gather back into its cause. The problem is not memory alone. Memory is part of a much larger physical network. When an event occurs, information spreads. Light carries an image outward. Sound moves through the air. Objects change position. People form memories. Electronic devices may record data. Heat is transferred. The event becomes linked with many parts of its environment. This spreading information makes the past difficult to erase completely. You can delete a photograph, but copies may remain. You can clean a footprint, but someone may have seen it. You can forget a conversation, but the other person may remember. An event may leave traces in places no one expected. The past becomes stable because it is redundantly recorded. Physicists sometimes describe this process using correlations. Two systems become correlated when the condition of one contains information about the condition of the other. A thermometer becomes correlated with the temperature of a room. A camera sensor becomes correlated with incoming light. A brain state becomes correlated with an experience. Once many systems become correlated with the same event, reversing all of them becomes overwhelmingly unlikely. This helps explain why the world appears to have a shared past. Different observers can compare records, photographs, documents, memories, and physical evidence may agree. They all developed from related interactions. Disagreement is possible because records are imperfect, but the basic direction remains the same. People may argue about what happened, yet they agree that the event they are discussing lies behind the present conversation. No one arrives at a meeting carrying verified minutes from next week's version of the same meeting. Considering the average usefulness of meeting minutes, this may not be a major loss, but it is still a clear feature of time. The relationship between memory and entropy becomes even clearer when we consider what the brain must do to remain capable of remembering. The brain is not a passive storage shelf. It is a living organ that constantly uses energy. Blood supplies oxygen and nutrients. Cells maintain electrical differences across their membranes. Chemical messengers are produced and recycled. Damaged components are repaired or removed. Keeping memories available requires ongoing physical work. Some memories are supported by changes in the strength of connections between neurons. When groups of neurons are repeatedly active together, their future responses can change. The network becomes more likely to reproduce part of the earlier pattern. Long-lasting memory can involve structural changes. New proteins may be produced. Connections may be altered. The organization of the network is modified. All of this happens inside the ordinary thermodynamic world. The brain takes in useful energy and releases less useful energy as heat. Its ability to store information depends on a flow from lower entropy resources toward higher entropy waste. A brain in complete equilibrium with its environment could not think, learn, or remember. It would have no usable energy differences to support activity. Conscious experience therefore depends on being far from equilibrium. The body continually maintains that condition through metabolism. This is one reason the mental arrow points with the thermodynamic arrow. Thinking is not detached from heat flow. Remembering is one of the processes made possible by it. There is also a close link between memory and the sense of personal identity. You experience yourself as a person who has moved through time because you can connect present awareness with earlier experiences. You remember places you have lived, skills you have learned, mistakes you would prefer to describe as useful trials, and relationships that shaped you. These memories create continuity. Without memory, the present would not feel like part of an extended life in the same way. There would still be immediate sensations, but the connection to a personal past would be weakened. The feeling that time flows may partly come from the continuous updating of memory. Each present moment becomes part of the recorded past. While attention moves to the next set of events, the brain does not experience all moments together. It receives information, processes it, and compares it with stored patterns. That sequence creates a strong impression of movement from what has happened toward what may happen. This does not necessarily mean that consciousness causes time to flow. It means that a conscious system built to form memories will naturally experience a direction. A creature in a universe with the opposite entropy gradient would likely call its own memory direction the past. It would remember events on the low entropy side of its present and anticipate events on the high entropy side. From our perspective, its processes might seem reversed. From its perspective, it would still feel as though memory pointed backward and uncertainty pointed forward. This shows that words such as past and future are connected to the direction in which records form. Observers define the remembered side as past because that is where the causes of their present information lie. The idea becomes stranger when applied to the entire universe. If every present record points toward lower entropy conditions, then the collective memory of the cosmos also points toward its early state. Light from distant galaxies shows us how they appeared long ago. Ancient radiation carries information from a much younger universe. Rocks preserve geological changes. Atomic nuclei contain evidence of processes inside earlier stars. The universe is filled with records. Astronomy is possible because light takes time to travel. Looking far into space means looking into the past. A nearby star is seen as it was years ago. A distant galaxy is seen as it was millions or billions of years ago. We never see those objects exactly as they are at the same instant according to our local clock. We see the information that has reached us. The night sky is therefore not a single present scene. It is a collection of records arriving from different times. Even the light from the sun is already several minutes old when it reaches Earth. If the sun were to change suddenly, we would continue seeing the earlier condition until the new light arrived. There is no way for the later event to create a memory here before its signal reaches us. Information has a limited speed. Causes must have time to produce effects at distant locations. This gives memory a connection not only to entropy, but also to causality. A physical record can form only when information from an event reaches the recording system. The cause and the record must be connected by some process. Light, sound, contact, electrical signals, or another interaction carries the influence. The order cannot be arbitrary. The event occurs, information travels, and the record forms. In relativity, different observers may disagree about the order of events that cannot influence one another, but when one event causes another, all observers agree on the causal order. The cause comes first along every valid description. Memory follows those causal links. You can remember an event only after information from it has affected your brain. This may appear to settle the matter completely, but memory raises another question. Why do we remember low-entropy states more often than high-entropy states? A broken glass contains evidence of the whole glass that existed earlier. The shapes of the fragments allow reconstruction. A whole glass does not normally contain visible evidence of the particular scattered arrangement it will have after breaking. The later state carries traces of the earlier one. Similarly, smoke contains information that fuel burned. Ash contains chemical evidence of combustion. A mature tree contains growth rings recording earlier seasons. An adult body contains marks of development and experience. Higher entropy states often contain records of lower entropy states because the processes that increased entropy created those records along the way. The reverse arrangement would require present records of future higher entropy events. For that to happen naturally, the universe would need unusual boundary conditions in the future, just as it appears to have unusual low entropy conditions in the past. Some speculative models consider a universe with special conditions at both ends of time. In such a universe, arrows might behave in unfamiliar ways. Records could be constrained by both boundaries. There is no evidence that our ordinary experience works that way. Everything we observe points toward a low entropy past and an entropy increasing future. Our memories are part of that evidence. Forgetting also fits into the same picture. Memories fade because the physical structures supporting them change. Connections weaken. New learning interferes with old patterns. Cells repair and replace components. Damage may occur. The brain does not preserve information perfectly forever because doing so would require reliable physical maintenance. Some memories last a lifetime, others disappear within minutes. Many remain in altered form. This is expected in a system that is active, limited, and constantly changing. Forgetting is not time running backward. It is another forward process that changes the present state of the brain. An erased recording does not mean the original event did not happen. It means one physical trace has been removed or overwritten. The erasure itself produces heat and leaves other consequences. Even deliberate forgetting, where it is possible at all, cannot restore the complete condition that existed before the event. The person has been changed by the effort. The surrounding world has moved on, and other records may remain. The arrow does not require perfect memory. It requires that records form from past interactions rather than future ones. Dreams sometimes make this distinction feel less secure. In a dream, the brain can create scenes that seem like memories of events that never occurred. It may combine familiar places, people, and emotions into a convincing experience. After waking, there can be a moment when the dream feels almost as real as yesterday. The brain can simulate possible worlds because imagination uses many of the same systems involved in memory. It rearranges stored information into new patterns. This does not give access to the future. A dream may later resemble an event by coincidence, or because the brain noticed clues and made a reasonable prediction. It is not a physical record created by the later event. The difference can be tested through reliable information. A true memory should be connected to evidence from an earlier cause. A prediction should be judged by whether it later proves accurate. The mind often blurs these categories because it is designed for useful action rather than perfect philosophical bookkeeping. Anticipation is especially interesting. You can imagine tomorrow in detail. You may picture a journey, rehearse a conversation, or worry about a problem that never arrives. These imagined futures can affect the body in the present. A person can become anxious about an event that has not happened. Heart rate may rise, muscles may tense, sleep may disappear shortly before an alarm that has not yet earned this level of hostility. The future image is still built from past information. The brain combines memories, expectations, and current signals to create a model of what may happen. The model influences the present, but the future event itself has not sent information backward. The causal chain remains ordinary. Past experience creates a prediction, and the prediction changes current behavior. Memory and anticipation point in opposite directions while using related machinery. One reconstructs from records, the other simulates from possibilities. This difference helps explain why the future feels open. Memory usually presents one experienced past, even if the details are uncertain. Imagination can produce many futures. You can remember taking one route home yesterday. Today you can imagine several routes, including one that avoids traffic, one that passes a shop, and one that seemed shorter until roadworks introduced a long practical lesson in regret. The present contains enough information to support multiple predictions. Only after one path is taken will new records identify what happened. That is the movement from possibility to evidence. The mind experiences it constantly. Expectations meet events. New information arrives. Memories are updated. The future becomes the recorded past. This process makes time feel directional at the personal level, but it also depends on a more general rule. Information must travel from causes to effects. A memory is one kind of effect, a footprint is another, a sound, a photograph, and a change in temperature are others. To understand why the universe arranges these links in the order it does, the next step is to look more carefully at causality itself. A falling cup breaks after it leaves the table. A switch is pressed before the lamp turns on. A message is sent before it is received. These sequences seem unquestionable, yet the underlying laws often connect events without using our everyday language of before and after. The direction becomes clear only when information moves, records form, and consequences spread into the surrounding world. A cup near the edge of a table does not need much encouragement. A small push, an elbow moving at the wrong moment, or a cat making a decision about gravity can be enough. The cup begins to fall, it strikes the floor. The material bends, cracks, and separates. Sound moves through the room. Tiny pieces scatter. Someone looks toward the noise and a new memory forms. Every part of that sequence seems to have a clear order. The push comes before the fall. The fall comes before the impact. The impact comes before the breaking. The sound reaches the listener after the cup hits the floor. The memory appears after the sound, and sight have affected the brain. This is what we mean by cause and effect. One event helps produce another. The cause lies earlier along the path of time, while the effect lies later. The order feels so basic that reversing it sounds absurd. We do not expect the sound of breaking pottery to travel backward through the air, gather at one point, pull fragments together, lift the repaired cup from the floor, and return it to a waiting hand. A film showing that sequence would be recognized as reversed immediately. The strange part is that the microscopic laws describing the individual particles may allow the reversed motions. Atoms in the cup, molecules in the air, and particles in the floor can follow paths that remain valid when their movements are reversed. The laws do not always contain an instruction saying that the cup must break in one direction and reassemble in the other. The direction appears when the entire event is considered, including the spreading of energy and information. Before the cup falls, its energy is organized. It has a particular position above the floor. The push gives it motion in a particular direction. During the impact, that organized energy is distributed among many parts of the environment. Some energy bends and breaks the material. Some becomes vibrations in the floor. Some moves the surrounding air and produces sound. Some becomes heat. Light reflects from the changing scene. Fragments move along different paths. The event leaves traces everywhere. A true reversal would require all those traces to return together. Vibrations would need to converge through the floor. Sound waves would have to gather from every part of the room. Heat would need to flow back into the exact microscopic motions of the cup. Every fragment would have to arrive at the right location with the right speed and angle. Nothing would be allowed to remain out of place. Even the observer would have to reverse. The brain activity that formed the memory would need to undo itself as the event ran backward. This is why cause and effect are closely connected to entropy. Causes produce effects while energy spreads and records form. The process moves from a more special condition toward a more probable one. The falling cup begins in a relatively restricted state. It is one object in one place. After the impact, there are many possible arrangements of fragments, vibrations, heat, and sound. The later condition can be produced in far more microscopic ways than the earlier one. We identify the earlier event as the cause, partly because it sits on the low entropy side of the sequence. The effect lies in the direction of increasing entropy. This relationship can be seen in simpler examples. Press a light switch and the lamp turns on. The movement of the switch changes an electrical connection. Current moves through the circuit. Energy reaches the lamp. Light and heat spread into the room. The effect does not happen before the physical signal can reach it. The lamp cannot respond to a switch that has not yet changed. There may be a delay too small for human senses to notice, but the sequence remains. Information about the switch must travel through the circuit before the lamp can react. Ring a doorbell, and an electrical signal moves from the button to the bell. The sound then travels through the air. A person hears it, forms a thought, and decides whether opening the door is wise. Each stage depends on information arriving from the previous one. Causality is not merely a habit of human storytelling. It is built into the way physical influence moves. Relativity places a strict limit on how quickly that influence can travel. No signal can move faster than light through empty space. This means that an event can affect only locations that its signals have had enough time to reach. Imagine a flash of light in a dark field. The light spreads outward. A nearby observer sees it first. A more distant observer sees it later. Until the light reaches them, the distant observer has no physical information about the flash. The event cannot cause a response at a distant location before any influence arrives. This creates a structure of possible cause and effect throughout space and time. Some events are close enough in space and time to be connected. Others are too far apart for either one to influence the other. Two observers may disagree about the order of events that have no possible causal connection. One observer may say that the first event occurred earlier, while another moving observer may say that the second event occurred earlier. This does not create a contradiction because neither event caused the other. No signal could travel between them in time. When two events are causally connected, every observer agrees on the order. If a signal travels from one event to another, the sending event comes first and the receiving event comes later. Relativity can make time flexible, but it does not allow an effect to arrive before its cause along an ordinary causal path. This protects the consistency of the physical world. A message cannot normally be received before it is sent. A warning cannot arrive before the danger that produced it. A person cannot use a reply to decide whether to ask the original question. If effects could freely travel into their own past, contradictions would appear. You could receive a message telling you not to send the message. If you obeyed, the warning would never be sent. Without the warning, you would send it after all. Physics treats such loops with great caution. Some unusual descriptions in general relativity allow paths that return to an earlier region of space and time, but whether those paths can exist in the real universe is uncertain. They may require conditions that nature does not permit. Ordinary cause and effect remain stable, because information moves forward along the same direction as entropy and memory. The word cause can still be difficult to define precisely. In daily life, we often use it loosely. We say rain caused the traffic caused the delay, and the delay caused someone to arrive at work carrying an excuse that had clearly been rehearsed. Each statement may be partly true, but events usually have many contributing causes. The cup breaks because it falls, because gravity accelerates it, because the floor resists its motion, because the cup is brittle, and because it was placed near the edge. Remove one condition, and the result might change. Physics often avoids choosing one single cause. Instead, it describes how an earlier state develops into a later state under particular laws and conditions. The state of the cup, the force of the push, the height of the table, and the material properties together determine what happens. Cause and effect emerge from the relationship between these states. Our minds simplify this. We identify the most useful or unusual factor and call it the cause. If someone knocks the cup, we blame the hand rather than gravity, even though gravity helped complete the event. Gravity was already present. The push was the new change. This way of selecting causes is useful for explanation and responsibility, but nature does not always divide events into neat pairs. A storm forms through changes in temperature, pressure, moisture, and air movement. A tree grows because of sunlight, water, nutrients, genetic information, and many chemical processes. A decision arises from perception, memory, emotion, and neural activity. Effects often come from networks of earlier conditions. Despite this complexity, the direction remains clear. The network expands from earlier conditions into later consequences. Information and energy spread through the system. Consider lighting a match. Friction at the match head produces heat. Chemical reactions begin. The flame releases more energy. Nearby air warms and rises. Light travels outward. Smoke forms and spreads. The match becomes ash. The cause is not one isolated instant. It is a sequence of connected processes. A reversed match would be remarkable. Smoke would gather from the room. Heat would leave the air and concentrate in the ash. Chemical products would reorganize into fuel. The match would cool as it became unburned. Individual particle motions might be reversed in an ideal description, but the full event requires an impossible level of coordination. The ordinary causal sequence follows the increase of entropy. This is also why effects often outnumber causes in visible complexity. A single action can produce many consequences. Drop one stone into water and countless molecules move. Ripples spread across the surface. Sound enters the air. The stone changes the bottom of the pond. Light reflects differently. An observer may remember the pattern. The event begins in a relatively concentrated form and becomes distributed. The reverse would require many independent-looking motions to converge into one exact action. Ripples from every direction would have to meet at the same point and launch the stone upward. Sound would return. The pond bed would restore itself. The forward sequence looks natural because it moves from one organized disturbance toward many spread-out effects. This pattern appears in communication. A person speaks, and sound waves spread across a room. Several listeners hear the same sentence. Each brain forms a slightly different record. The information may then be repeated, written, or misunderstood in creative ways. One cause can create many records. Recovering the original event from those records may be possible. but reversing the event physically is not the same as reconstructing it mentally. A recording can play a voice again, but it does not cause the speaker to unsay the words. The recording is a new cause producing new sound. It copies information without reversing time. This distinction matters because humans often reverse sequences in thought. We can watch a film backward, retell a story from the ending, or reconstruct an accident from evidence. Our reasoning can move from effects to possible causes. Detectives do this. Scientists do it. Anyone discovering an empty biscuit tin may attempt it. The investigation runs backward in logic, but the physical process of investigation still runs forward in time. Evidence enters the senses. The brain changes. Notes are written. A conclusion forms later. We infer the past from present effects, yet the act of inference produces new effects in the future. Scientific experiments depend on this structure. Researchers prepare a system, allow it to change, and measure the result. They compare different starting conditions and look for reliable patterns. If changing one factor repeatedly changes the outcome, that factor may have a causal role. Careful experiments try to separate true influence from coincidence. This is not always easy. Two events can be related without one causing the other. Ice cream sales may rise at the same time as sunburn cases. Buying ice cream does not usually cause sunburn. Warm, sunny weather influences both. Causality requires more than events occurring together. There must be a physical or logical pathway through which one can affect the other. In fundamental physics, that pathway is carried by interactions. Particles exchange energy and motion. Fields influence matter. Signals travel through space. Every effect must be connected to something that can produce it. Quantum mechanics makes the picture less familiar, but does not remove the need for causal consistency. Quantum systems can show correlations that have no classical explanation, especially when particles are entangled. Measurements on entangled particles can be strongly related even when the particles are far apart. The correlations appear immediately in the mathematical description, which once led to worries about faster-than-light influence. These correlations cannot be used to send a controllable message faster than light. An observer cannot choose a result on one side and force a readable signal to appear on the other. Ordinary communication still requires a signal travelling within the limits set by relativity. Quantum theory changes what can be predicted about outcomes, but it does not provide a convenient service for sending tomorrow's lottery numbers to yesterday. At the quantum level, causes may determine probabilities rather than one certain result. Prepare the same kind of system many times, and different outcomes may appear. The theory predicts how often each result should occur. The cause is then connected to a pattern of possibilities. This raises an important question about whether every event has a definite cause. Some interpretations of quantum mechanics say that individual outcomes are fundamentally random. Others describe a larger structure in which all possible outcomes occur in different branches. The debate continues, but the direction of records remains. A measurement produces an outcome. The apparatus changes. The environment becomes connected with the result. An observer forms a memory. These later records do not appear before the measurement interaction. The quantum event becomes part of history through the same process that gives ordinary events their stability. Information spreads into many surrounding systems. This spreading is sometimes called decoherence. A quantum system interacts with its environment, and delicate combinations of possibilities become difficult to observe. The environment effectively records information about the system. A particle may interact with light, air, or a measuring device. Those interactions distribute information. Reversing them would require controlling an enormous number of environmental details. The process resembles thermodynamic irreversibility. A small event becomes linked with a large world. That link turns a fragile possibility into a durable fact for practical purposes. The cup either breaks or it does not. Once the result has affected the floor, air, light, camera, and observer, the event has become widely recorded. The possibility of reversing every connection becomes negligible. Causal order is therefore reinforced by the production of records. An effect carries information about its cause, then creates further effects of its own. This gives history a branching shape. One event influences several later events. Each of those may influence many more. A conversation changes a decision. The decision changes a journey. The journey creates new encounters. Small causes can sometimes produce large consequences because complex systems amplify differences. Weather is a familiar example. A tiny change in atmospheric conditions can influence how a storm develops. This sensitivity is often called the butterfly effect. The phrase does not mean that every butterfly creates a hurricane. It means that in certain systems, very small differences in starting conditions can grow over time. Prediction becomes difficult because no measurement is perfectly exact. A small uncertainty today may become a large uncertainty later. This gives cause and effect another imbalance. We can often explain an event after it happens more easily than we can predict it before it happens. After a storm develops, we can study the path it took. Beforehand, many paths may have been possible within our limited knowledge. The past has records, the future has probabilities. Human choices belong to this same world. A decision becomes a cause that changes later events. It may be influenced by earlier experiences, current needs, and expectations about the future. Once the action occurs, it creates consequences that cannot be fully withdrawn. An apology can repair part of the damage, but it does not erase the original event. A corrected message does not remove every copy of the first one. A repaired cup is not identical to an unbroken cup. The arrow of time gives actions weight, because effects persist. This is not only a philosophical statement, it is physical. Information spreads, bodies change, and environments record what happens. The inability to rewind does not mean nothing can be restored. Broken objects can be repaired. Illnesses can be treated. Mistakes can be corrected. A cold drink can be warmed. Restoration requires new causes and new energy. It creates a later condition that resembles an earlier one without reversing the entire history between them. Glue can join fragments, but the repaired cup contains seams. Heating can return a drink to its former temperature, but the energy comes from another source and increases entropy elsewhere. The world can revisit similar conditions, but it does not travel backward along the exact path. This is why repeated events are never completely identical. A pendulum may return to the same position, but the room has changed slightly. Energy has been lost as heat. The clock has advanced. The observer has formed new memories. Cycles occur within a larger one-way history. Day follows night, seasons return, and planets orbit. These regular patterns may look like repetition, but each cycle takes place at a later time. Earth does not return to the exact same state after one orbit. The sun has used more fuel, light has travelled farther, living things have changed. Even a clock that returns its hands to the same numbers is not returning the universe to an earlier moment. It is marking another point in an ongoing sequence. Cause and effect keep that sequence connected. Each state carries consequences from previous states and creates conditions for what follows. There is another reason the falling cup makes such a useful example. The process is easy to see, but it contains several different kinds of causation at once. Gravity changes the cup's motion. Contact with the floor changes its shape. Internal forces determine where cracks begin. The arrangement of the material determines how those cracks spread. Collisions with the air produce sound. Light from the scene reaches the eyes. Neural activity produces perception and memory. No single link explains the whole event. The effect is a chain in which each stage becomes the cause of the next. Chains of this kind exist at every scale. Inside a cell, one chemical reaction changes the conditions for another. In an ecosystem, The growth of one population affects the food available to another. In a star, gravity raises pressure and temperature until nuclear reactions begin. The energy released by those reactions changes the structure of the star. Nature develops through connected changes. The direction of those chains may seem to come from the fact that one event must be completed before the next can begin. The cup must reach the floor before the floor can resist it. The chemical fuel must react before heat can spread. That's true, but it does not fully explain why the entire chain points the way it does. A reverse chain would also contain an order. Sound would gather before fragments joined. Fragments would join before the cup rose. The cup would rise before the hand received it. The deeper difference is that the reverse chain begins with a highly coordinated environment. Countless scattered effects must act together to create one concentrated event. The forward chain does not require that preparation. A simple local cause can spread its influence widely. This creates an imbalance between explanation and preparation. It is easy to arrange a cup so that it falls. It is unimaginably difficult to arrange an entire room so that a broken cup naturally reassembles. Both outcomes may be consistent with reversible microscopic laws, but only one begins from conditions we commonly find. The arrow of causality therefore depends on the kinds of boundary conditions present in the universe. The low-entropy path supplies simple causes whose effects can spread. It does not supply the delicately coordinated future conditions needed for effects to gather into earlier causes. This can be understood by imagining two kinds of room. In the first room, a cup sits on a table. The air moves randomly, the floor is still, the walls are at an ordinary temperature. A hand pushes the cup. Nothing else needs to be prepared. In the second room, broken fragments lie on the floor. To make the cup rise and reassemble without direct intervention, every molecule in the room must be arranged with astonishing precision. Air currents must push the fragments correctly. Vibrations in the floor must meet at the right points. Heat must move in carefully directed ways. The second room may look ordinary from a distance, but its microscopic condition would be more carefully arranged than any machine humans have built. That hidden preparation would itself be the true cause of the apparent reversal. If such a reversal occurred, we would not have discovered an effect coming before its cause. We would have found a different cause concealed in the exact arrangement of the environment. This is an important lesson. Strange outcomes do not necessarily remove causality. They may reveal that we failed to notice the relevant earlier conditions. A magician appears to make an object move without a cause. The cause is present, but hidden by the performance. A sudden medical symptom may seem uncaused until an underlying process is discovered. A machine may stop without an obvious reason until a damaged component is found. Science often advances by locating causes that were previously invisible. There are limits to this approach. Quantum outcomes may not have hidden causes of the ordinary kind. Some events may be genuinely probabilistic. Even then, they occur within a causal structure. The preparation of the system affects the possible outcomes, and the outcome affects later records. Causality does not always mean that one earlier event fixes one later event with certainty. It can mean that earlier conditions constrain what may happen. A loaded die does not determine one result before every throw, but its shape and weight distribution affect the probabilities. A weather system does not guarantee one exact raindrop pattern, but atmospheric conditions constrain the storm. Causes can shape possibilities without selecting every detail. This is especially useful when thinking about complex systems. A person's health, behavior, or future cannot usually be traced to one cause. Many influences combine, and chance may play a role. The arrow still runs from existing conditions toward later outcomes. New information is created as one possibility becomes actual. Once the outcome has occurred, records make it part of the past. The result may influence what happens next, becoming another cause in a longer chain. This is how the universe builds history without needing a visible clock to push it along. Events interact, consequences spread, records accumulate. Each moment inherits conditions from what came before, yet this still leaves a larger question. The arrows of entropy, memory, and causality all appear to point in the same direction, because the universe began in a special condition. But the universe is not static. Space itself is expanding, distant galaxies are moving apart, and the cosmos has changed from a hot, dense beginning toward a colder and more spread out future. It is natural to ask whether that expansion is merely another process happening within time, or whether it helps establish the direction we call forward. A cooling cup has a nearby environment into which heat can spread. The entire universe has no outside room waiting around it. Its large-scale evolution must be understood through the changing geometry of space, the formation of structure, and the way energy behaves as the cosmos grows. The next step is to move from falling cups and ringing doorbells to the largest causal system available, the universe itself, and ask whether the widening distance between galaxies provides time with a cosmic direction. The universe is expanding. Distant galaxies are, on average, moving farther away from one another, and the space between large groups of galaxies is growing. This expansion has been happening for billions of years. When we look into the distant past, we see a universe that was hotter, denser, and more uniform than the one around us today. That gives the history of the cosmos an obvious-looking direction. Earlier means smaller, hotter, and denser. Later means larger, cooler, and more spread out. It is tempting to stop there and say that expansion is the reason time points forward. The universe grows, so time moves in the direction of that growth. The past lies toward the smaller universe, while the future lies toward the larger one. The connection is not quite that simple. Expansion gives us a reliable way to distinguish different eras, but it does not automatically explain every feature of time's direction. A clock inside an expanding universe still needs a physical process to mark change. A broken glass still needs an explanation for why it does not reassemble. A brain still needs a reason for remembering earlier events instead of later ones. The expansion of space and the increase of entropy are related, but they are not identical. To see the difference, imagine an ordinary rubber sheet marked with many small dots. As the sheet stretches, every dot moves farther from most of the others. The dots themselves do not need to travel across the material between them grows. This picture is often used to describe cosmic expansion. Although the real universe is not a sheet stretching into an empty room, space does not need an outside area to expand into. The distances within space change. A better everyday comparison might be a loaf of bread rising in an oven. Imagine raisins scattered throughout the dough. As the loaf expands, each raisin sees the others moving farther away. No raisin is the center of the expansion. The dough grows everywhere. The comparison has limits, especially because the universe does not appear to be rising in a cosmic oven, which is probably reassuring. It does capture the idea that expansion happens throughout space, rather than from one central point. From any large galaxy, most sufficiently distant galaxies appear to be receding. The farther away a galaxy is, the faster the distance between us and that galaxy tends to grow. This does not mean that every object is expanding. Atoms do not swell with the universe. People do not become taller because space has had a productive afternoon. The forces holding atoms, bodies, planets, and galaxies together are far stronger at those scales. The expansion becomes important across enormous distances, where gravity has not bound matter into one stable system. Our galaxy remains held together. The solar system remains held together. A cup remains the same size while sitting on a table, at least until the cat becomes involved again. Between distant groups of galaxies, however, the amount of space grows. If we run the cosmic history backward, those galaxies move closer together. Matter becomes denser. Radiation becomes hotter. Eventually, we reach an early period when the visible universe was in a much more compressed condition. The phrase Big Bang can create the wrong picture. It was not an explosion from one location into an existing emptiness. It was an early state in which space itself was expanding, and matter and energy were extremely hot and dense throughout the observable region. There was no central point from which everything flew outward. Every large region was once closer to every other large region. The expansion has cooled the universe. Light travelling through expanding space becomes stretched to longer wavelengths. Its energy decreases. The hot radiation of the early cosmos has become the much colder background radiation that astronomers observe today. The cooling provides another clear difference between past and future. The young universe was filled with energetic radiation. The present universe is far cooler. In the distant future, it is expected to become cooler still as expansion continues. Stars temporarily resist this cooling trend by creating hot local regions. They form when gravity pulls gas together, raising the pressure and temperature until nuclear reactions begin. These reactions release energy, and stars shine into the colder space around them. That temperature difference allows entropy to increase. Concentrated energy leaves the star and spreads outward as radiation. A star does not reduce the overall direction of cosmic change. It creates a local source of useful energy while turning nuclear fuel into more spread out forms. Earth depends on one of these sources. The Sun sends relatively concentrated energy toward our planet. Earth absorbs it, uses part of it to drive weather and life, then releases energy back into space in a more spread out form. The universe's expansion helps provide the cold surroundings into which that energy can travel. In this way, expansion supports the thermodynamic arrow. It creates and maintains differences that allow processes to occur. A static universe that had already reached one uniform temperature would offer far fewer opportunities for change. There would be no hot stars shining into cold space, no large energy flows, and no planets receiving usable radiation. Expansion prevents the universe from settling quickly into complete equilibrium. As space grows, matter becomes more separated, radiation becomes cooler, and new structures can form under gravity. This sounds slightly contradictory. Expansion pulls distant regions apart, while gravity pulls nearby matter together. Both processes occur at the same time. On the largest scales, space expands. Within regions where matter is dense enough, gravity can overcome that expansion and gather material into stars and galaxies. The result is a universe that becomes emptier overall, while also becoming more structured in particular places. The early cosmos was smoother. Matter and radiation were distributed with only small variations. Over time, gravity amplified those variations. Slightly denser regions attracted more matter. They grew into larger clumps. Those clumps eventually formed the broad network of galaxies seen across the universe today. Large groups of galaxies gather in long structures, while enormous empty regions lie between them. Matter has become much less uniform than it was in the early universe. This growth of structure is essential for understanding cosmic entropy. In an ordinary box of gas without strong gravity, an even distribution is usually a high entropy condition. The gas spreads until it fills the box uniformly. Gravity changes the situation because gravity attracts. A smooth distribution of gravitating matter can contain the potential for much greater change. Matter can collapse, heat up, form stars, release radiation, and produce black holes. The smooth early universe was therefore very special. It had low gravitational entropy even though matter was spread evenly. As gravity formed structures, the total entropy increased. A collapsing cloud of gas becomes smaller and more organized in appearance, but it releases energy. Particles move faster, the cloud heats, radiation escapes, a star may form. Visible order increases locally while energy spreads through the wider environment. This is the same general pattern seen in living organisms and weather systems. Structure can form when there is an energy flow that increases total entropy. The most dramatic contributors to gravitational entropy are black holes. A black hole forms when enough matter is concentrated into a sufficiently small region. its gravity becomes so strong that beyond a boundary known as the event horizon, nothing can return to the outside. Black holes have enormous entropy. The amount is related to the size of the event horizon, rather than simply the volume inside. This was a surprising discovery, because black holes were once treated as simple objects that swallowed information and offered little else to study. The connection between black holes, entropy, and temperature revealed that they obey thermodynamic rules. A black hole can even emit an extremely weak form of radiation and slowly lose mass. For large black holes, the process takes an almost unimaginable amount of time. The formation and eventual development of black holes provide a major route through which cosmic entropy can grow. This helps answer an important question. If the early universe was hot and dense, why was its entropy not already at the highest possible level? The reason is that matter had not yet collapsed into the wide range of structures allowed by gravity. The early smoothness was an unusually restricted condition. There was enormous room for future gravitational change. The universe began with a large difference between what it was and what it could become. That difference gave entropy somewhere to go. Expansion made it possible for the universe to cool and for matter to separate into regions where gravity could form structures. Stars, galaxies, planets, and black holes emerged within this developing cosmos. The arrow of time may therefore be tied not merely to expansion, but to expansion combined with an extremely special beginning. Suppose a universe expanded but began in complete equilibrium. It might grow larger, but there would be little useful energy difference and few irreversible processes. Expansion alone would label one direction as larger, but observers inside it might not experience a strong thermodynamic arrow. Suppose instead that a universe contracted. Would time reverse? Not necessarily. A contracting universe would become smaller and denser, but entropy could continue increasing during the contraction. Stars could age, memories could form, and causes could still produce effects in the same experienced direction. The size of the universe and the direction of entropy do not have to match automatically. For many years, some scientists wondered whether the arrow of time might reverse if cosmic expansion ever changed into contraction. In that picture, broken objects might reassemble, and people might remember what we currently call the future as the universe moved toward a final collapse. This idea is not required by known thermodynamics. A contracting universe would probably continue developing higher entropy. Structures would collide, radiation would heat, and black holes could merge. The approach to a dense final state would not simply replay cosmic history backward. A film of the universe contracting would not look like a backward film of expansion, unless every microscopic motion and every record were also reversed. Changing the overall scale is not enough. Current observations indicate that cosmic expansion is accelerating rather than slowing toward a future contraction. Distant galaxies are separating at an increasing rate because of something described as dark energy. The name dark energy tells us less than it may appear to. It is a label for whatever is causing the expansion to accelerate. Its underlying nature remains uncertain. It does not behave like ordinary matter gathered into objects. It seems to be associated with space itself and becomes important across very large distances. As the universe expands, matter becomes more diluted. The effect linked to dark energy does not appear to weaken in the same way, so it increasingly dominates cosmic evolution. If this acceleration continues, distant galaxies outside our local gravitational group will eventually move so far away that their light will no longer reach us. Future observers in our region may see a much emptier sky. The evidence for the wider expanding universe could become difficult to detect. Our own group of galaxies will remain gravitationally connected. Nearby large galaxies are expected to merge over immense periods. Stars will continue to form for a time, then the available gas will gradually run low. Existing stars will age. Some will end as dense remnants. Others will collapse into black holes. The universe will become darker as fewer stars shine. This possible future is often associated with heat death. The name sounds like a dramatic final event, but it refers to a gradual approach toward a state where useful energy differences are greatly reduced. Heat death does not mean that every part of the universe reaches one warm temperature. In an endlessly expanding universe, the overall temperature may become extremely low. The word heat refers to thermodynamics. The important point is that energy becomes too spread out to perform much organized work. Stars provide concentrated energy because they are hot compared with their surroundings. Once stars are gone and matter has decayed or become trapped in remnants, fewer such differences remain. Black holes may eventually evaporate. Radiation continues to stretch as space expands. Particles become widely separated. The universe approaches a condition with high entropy and very little available energy for creating new structure. Time would still exist in physical descriptions, but few events would provide clocks, memories, or observers. A nearly empty universe might continue for an extraordinary duration with only rare interactions. This future gives cosmic expansion a close relationship with the arrow of time. The universe moves from a special low-entropy beginning toward a more diluted higher entropy condition. Expansion is part of the route, but the initial low-entropy state remains the deeper source of the direction. The Big Bang did not merely place matter close together. It placed the universe in an arrangement that was remarkably smooth and capable of developing into countless later forms. That condition is one of the largest unexplained facts in physics. Cosmology can describe much of what happened after the early period. It can track expansion, cooling, the formation of atoms, the growth of galaxies, and the appearance of stars. It is much harder to explain why the starting state had such low entropy. One possibility is that a deeper law required it. Another is that our observable universe emerged from a larger process that selected or produced special initial conditions. Some models propose earlier phases before the hot dense period. Others suggest cycles of expansion and contraction. There are ideas involving quantum events, multiple universes, or conditions in which the ordinary concept of before no longer applies. None of these possibilities has provided a final explanation. The question becomes especially difficult because any explanation of the beginning seems to require another condition behind it. If a prior process created the low-entropy universe, why did that prior process have the properties needed to do so? Moving the starting point does not always remove the puzzle. There is also a limit to how confidently we can use ordinary time near the beginning. General relativity describes space and time together. As we approach the earliest conditions, densities and temperatures become so extreme that quantum effects should become important. General relativity does not contain a complete quantum description of space-time. Quantum mechanics, in its usual form, treats time differently from general relativity. Without a successful theory combining them, our description of the earliest universe remains incomplete. The question of where time gets its direction may therefore require an answer from quantum gravity, a theory that does not yet exist in finished form. Even so, the expansion we observe gives strong evidence for a historical direction. Light from distant galaxies is stretched by expanding space. The amount of stretching tells astronomers how much the universe has changed while the light travelled. Very distant objects are seen as they existed when the universe was younger. Their light forms a record of cosmic history. Astronomers do not watch the universe develop over billions of years in real time. They look across distance and receive light from different eras. Nearby galaxies appear more recent. Farther galaxies appear younger. The deepest observations reveal the early stages of galaxy formation. A telescope becomes a machine for reading old light. This does not allow us to look into the future. Light from future events has not been emitted and cannot have reached us. Once again, the cosmological arrow aligns with the arrow of records. The expanding universe sends us evidence from earlier states. The background radiation is one of the oldest records available. It comes from a time when the universe had cooled enough for light to travel freely across great distances. Before that transition, charged particles scattered light repeatedly. The universe was similar to a dense glowing fog. When atoms formed, light could move more freely. That ancient radiation has travelled ever since, stretching and cooling as space expanded. Its small variations preserve information about the early distribution of matter. Those variations later grew into galaxies and larger structures. The sky contains a record of the conditions from which the visible cosmos developed. That record points in the same direction as fossils, memories, and broken objects. Present evidence leads toward an earlier, lower entropy state. The expansion also changes which events can influence one another. As distant regions separate faster, signals may never cross the growing distance. Parts of the universe can pass beyond one another's future reach. This creates cosmic horizons. There are regions we can observe because their past light has reached us, yet signals sent now may never reach them. Other regions may be forever unobservable because their light will never arrive. The causal structure of the universe depends on its expansion. A signal does not simply travel through a fixed background. The space it crosses changes during the journey. Imagine walking toward a destination while the path beneath you stretches. If the stretching is slow, you still arrive. If it becomes fast enough, the destination may remain out of reach even though you continue moving. Light faces a similar problem across cosmic distances. Locally, it always travels at the same speed. Globally, expanding space can increase the separation so quickly that the light never reaches the intended region. This means the future universe may become divided into isolated areas. Each gravitationally bound region will lose contact with most others. Information that could once have crossed between them will no longer be able to do so. The expansion therefore affects not only temperature and structure, but the spread of causes and information. It decides which events can leave records in which places. Our current view of the cosmos is possible, because light from many distant regions has had time to arrive. We live during an era when galaxies are bright. The background radiation is measurable, and evidence for cosmic history remains visible. This may be a temporary privilege. Far future observers may have accurate local physics, but little direct evidence that the universe once contained billions of visible galaxies. Expansion will have carried much of that evidence beyond reach. Their present will contain fewer records of the larger cosmic past. This does not reverse the arrow. It shows that records can become inaccessible even while entropy continues increasing. Information may spread so widely that no local observer can recover it. The same principle appears in smaller systems. Heat spreads through a room, but measuring the exact path of every molecule becomes impossible. Sound travels away and weakens. A written record can decay. The universe keeps its history in physical correlations, but those correlations do not always remain available to a particular observer. Expansion can hide records without erasing the overall causal sequence. At this point, the broad picture begins to take shape. The universe started in a hot, dense, smooth, low-entropy condition. It expanded and cooled. Gravity formed structure, stars released energy, galaxies developed, black holes formed, entropy increased. The thermodynamic arrow points away from the special beginning. Memory points toward that beginning because records are created as entropy rises. Cause and effect follow the same direction because influences spread from simpler local conditions into wider consequences. Cosmic expansion supports this process by cooling radiation, separating distant regions and allowing structure to develop. Still, one difficulty remains. The large-scale universe gives time a clear historical orientation, but the smallest known physical systems do not always show the same preference. At the quantum level, many processes can occur in ways that look almost identical when their time order is reversed. Particles can move through several possibilities. Measurements introduce probabilities. The the basic equations often fail to explain why one moment should be called earlier and another later. The cosmic arrow is strong because the universe contains enormous numbers of interacting particles and a low entropy past. Quantum physics asks what happens before those large-scale patterns are formed. That is where the direction becomes uncertain again, not because broken cups begin repairing themselves, but because the fundamental description may contain no obvious instruction telling reality which way time should point. At the smallest known scales, the direction of time becomes much harder to see. The ordinary world is filled with events that clearly distinguish before from after. Ice melts, smoke spreads, bodies age, stars use their fuel. A dropped cup reaches the floor before it breaks. Quantum physics, however, describes matter in a way that often looks almost the same when the order of events is reversed. This does not mean that atoms routinely travel into the past, or that particles keep tiny time machines in places scientists have not checked. It means that many of the basic rules used to predict quantum behavior do not contain the strong forward preference that appears in daily life. A particle can move from one condition to another. If the motion is reversed carefully, the opposite process may also be allowed. The description connects possible states without always telling us which one must be called the beginning. This is similar to the simple collision of two smooth balls. Watch them approach, collide, and move apart. Reverse the recording and the result can still look reasonable. Quantum events often have this same quality. Although the objects involved do not behave like tiny solid balls, they behave according to probabilities. Before a measurement, a quantum system may not have one definite value for everything we could ask about it. Instead, the theory describes several possible outcomes and the likelihood of each one. That is already very different from ordinary experience. A cup on a table appears to have one location. We do not expect it to be partly on the table, partly under the sofa, and partly inside a cupboard that has not been opened since someone bought a fondue set. A quantum particle can be described as having several possible locations until it interacts strongly enough with another system to leave a record. This does not mean that the particle is secretly choosing one ordinary location while refusing to tell us. Some interpretations allow that possibility, but standard quantum predictions do not require it. The theory works by treating the alternatives as part of one quantum state. The different possibilities can influence one another. They can combine, cancel, and produce patterns that would be impossible if the particle had simply followed one hidden path. This behavior is called interference. It is one of the clearest signs that quantum possibilities are not merely ordinary ignorance. Imagine sending individual particles toward a barrier containing two narrow openings. A screen waits behind the barrier to record where each particle arrives. If the particles were ordinary grains of sand, each one would pass through one opening or the other. Over time, the screen would show two broad piles. Quantum particles can create a striped pattern instead. Regions with many arrivals alternate with regions containing fewer. The pattern resembles what happens when waves overlap. Even when particles are sent one at a time, the pattern gradually appears. Each particle arrives at one definite point, but the distribution of many arrivals reflects interference between possible paths. The quantum description includes both openings. The alternatives affect the final probabilities. The strange part for time is that this process can often be described in either direction. A particle travels from the source, interacts with the barrier, and reaches the screen. Reversing the process gives a particle leaving the screen, interacting with the barrier, and returning toward the source. The reversed sequence may be unusual to arrange, but the underlying quantum rules can still allow it. Once the particle leaves a visible mark on the screen, however, the situation changes. The mark is not one isolated quantum event. It involves atoms in the screen, energy transfer, light, heat, and perhaps a measuring device connected to a computer. Information about the result spreads into the environment. The particle may have begun in a delicate combination of possibilities, but the measurement creates a durable record. One spot darkens. An electrical signal forms. A file is stored. A scientist looks at the result and decides whether it was interesting enough to justify the hours spent aligning the equipment. The full process now has a clear direction. A prepared quantum state becomes a recorded outcome. Reversing that complete event would require far more than sending one particle backward. Every atom in the screen would need to return to its earlier condition. The electrical signal would need to undo itself. Heat would have to gather. The computer record would need to disappear through an exact reversal of its physical changes. The scientist's memory would also need to unwind. Quantum laws may allow reversible motion for a small isolated system. Measurement connects that system to an enormous environment, and the familiar arrow appears. This connection is often described through decoherence. Decoherence occurs when a quantum system interacts with its surroundings. Information about the possible state spreads into air molecules, light measuring devices, and other nearby matter. The alternatives do not simply vanish. They become entangled with different states of the environment. Entanglement is a quantum relationship in which systems can no longer be described independently. The condition of one is connected with the condition of another, even when the systems later move far apart. Suppose a particle can take two possible paths. If the environment records which path occurred, the particle becomes linked with different environmental conditions. One set of surrounding particles carries information about the first path. Another carries information about the second. To observe interference again, every trace of that path information would need to be removed. The environment would have to forget which path was taken. For a carefully controlled experiment involving only a few particles, researchers can sometimes reduce those interactions and preserve quantum interference. For a large object in an ordinary room, environmental recording happens almost immediately. Light reflects from it. Air molecules collide with it. Heat moves between it and the surroundings. The object's position becomes copied into countless nearby systems. This is why a table does not appear in several locations at once. It is continuously interacting with the environment. Information about where it is spreads too quickly for its alternatives to interfere in any noticeable way. The table behaves classically, not because quantum physics stops applying, but because its quantum possibilities have become linked with an uncontrollable number of surrounding details. Decoherence explains how the ordinary world emerges from quantum rules. It also helps explain why quantum events acquire a direction. A delicate quantum state can spread information into the environment easily. Gathering all that information and restoring the original state is overwhelmingly difficult. The process resembles ink spreading through water. Each microscopic interaction may be reversible, yet the complete reversal would require impossible coordination. Quantum mechanics, therefore, does not remove the thermodynamic arrow. It shows how that arrow can develop as small systems become connected with larger ones. This still leaves a difficult question about measurement. The quantum description provides probabilities for different outcomes. A detector then records one result. Why does one possibility become the event that enters history? Different interpretations of quantum mechanics answer this in different ways. One traditional approach says that measurement causes the quantum state to collapse. Before the measurement, several outcomes are possible. Afterward, only the observed result remains. Collapse appears to introduce a direction. A spread of possibilities becomes one definite record. The reverse process, one definite record becoming the original combination of possibilities, does not normally occur. The difficulty is that collapse is not described in the same way as ordinary quantum evolution. It looks like a separate rule added when a measurement happens. But what counts as a measurement? A detector clearly measures. A camera can measure. A molecule interacting with another molecule may also carry away information. The boundary between quantum system and measuring device is not always obvious. Another interpretation avoids collapse. It says that all outcomes continue in different branches of the total quantum state. When a measurement occurs, the observer becomes entangled with the system. In one branch, the observer records one result. In another branch, the observer records a different result. Each version experiences one definite outcome because the branches no longer interfere in any practical way. This is known as the many worlds interpretation. The name suggests a collection of separate universes arranged like rooms in a very ambitious hotel, but the idea is more precise. It treats the total quantum state as continuing without collapse, while interactions produce branches that behave independently. In this view, the underlying quantum rules remain reversible. The apparent direction comes from branching, decoherence, and the increase of entanglement with the environment. The future contains more separated records than the past. A simple quantum state develops into many correlated states. Reversing the process would require those records to converge and interfere again with perfect accuracy. Other interpretations propose hidden variables, spontaneous collapse, information-based descriptions, or relationships that exist only between systems. Each approach tries to explain how definite events arise from quantum possibilities. No interpretation has achieved universal agreement. The predictions used in experiments are extremely successful. The disagreement concerns what those predictions say reality is doing when no one is measuring it. This makes quantum time unusual. The theory tells us how probabilities change, but the meaning of the change depends partly on interpretation. There is another complication. In ordinary quantum mechanics, time is treated differently from position. Position is part of the quantum system. A particle can have several possible positions. Time usually remains an external parameter. It tells us when the quantum state is being described. A clock outside the system appears to mark a steady sequence. This resembles the older Newtonian view in which time provides a fixed background. The quantum state changes while time itself remains untouched. General relativity does not treat time that way. In relativity, time is part of space-time. It can pass at different rates depending on motion and gravity. It is influenced by matter and energy. Place a clock near a massive object, and it runs more slowly compared with a clock farther away. Move a clock at high speed, and its elapsed time differs from that of a slower clock. Time is dynamic and connected with the geometry of the universe. Quantum mechanics and general relativity therefore begin with different ideas about time. One uses time as a background for quantum change, the other makes time part of the physical system that can bend and respond. Both theories work extremely well in their own domains. Quantum mechanics describes particles, atoms, and microscopic interactions. General relativity describes gravity, planets, stars, black holes, and the large-scale universe. The problem appears when both are needed at once. Near the center of a black hole, matter is compressed into extreme conditions. In the earliest universe, density and temperature were enormous. Gravity was strong, but quantum effects were also essential. A complete description requires a quantum theory of gravity. Researchers have developed several possible approaches, but no final theory has been confirmed by experiment. One of the hardest issues is known as the problem of time. When scientists try to describe the entire universe quantum mechanically, there is no external clock standing outside it. The universe includes every clock, every observer, and every physical process. What can measure the change of the whole universe from the outside when there is no outside? Some attempts to combine quantum mechanics with gravity produce a description in which time disappears from the central equation. The universe is represented by relationships among possible configurations, but no external time variable tells those configurations how to evolve. The result looks timeless. This does not mean that nothing happens. It means that change may need to be described by comparing one part of the universe with another. A clock is itself a physical system. Its hands move, its crystal vibrates, or its atoms change state. We call those changes time only because they are regular and can be compared with other changes. Perhaps time is not a separate substance flowing through the universe. Perhaps it is a way of describing how physical systems change relative to one another. Imagine a completely empty universe containing only one object that never changes. There would be no clock, no motion, and no sequence of records. Asking how much time had passed would have no practical answer. Add a second changing object, and comparison becomes possible. One system can act as a clock for the other. A planet completes an orbit while an atom undergoes many repeated changes. A person grows older while a calendar advances. One process is measured against another. In quantum gravity, time may arise from these internal relationships. One part of the universe can serve as a clock. The state of another part can then be described relative to it. This is sometimes called relational time. Instead of saying that a system changes in an external time, we say that one variable changes when another variable takes a particular value. No mathematical formula is needed to understand the basic idea. A child becomes taller while the seasons change. The two processes are compared. Time is the structure connecting them. This approach may explain how an apparently timeless universe can contain observers who experience change. The total description could remain fixed, while different parts contain correlations that look like a sequence from inside. A book provides a rough comparison. The whole book exists as one object, every page is present. Yet a reader encounters the story in order, one page after another. The comparison has limits because a reader exists outside the book and chooses the sequence. The universe may have no outside reader. Still, it shows how a complete structure can contain ordered relationships without needing the whole object to move through another time. Some physicists suggest that the flow of time is not fundamental. It may emerge from the way information, entanglement, and entropy change within a larger quantum structure. Entanglement may be especially important. When quantum systems interact, they become correlated. As more systems interact, the network of entanglement can grow. This growth often follows the same direction as entropy. A simple initial state develops into a more connected one. Information becomes distributed across many parts of the system. An observer inside that process can form records only in the direction of increasing entanglement. Memories become linked with earlier events. Measurements create correlations. The environment stores copies of information. The direction of time could arise from the growth of these relationships. This does not mean entanglement alone solves the problem. A quantum system can sometimes lose entanglement as well as gain it. Carefully controlled operations can reverse certain interactions. The larger question is why the universe began in a state with relatively low entropy and limited entanglement, allowing both to increase. Once again, the special beginning returns. Quantum physics may explain how the arrow develops from interactions, but it still needs an initial condition that is different from later conditions. Without that difference, there may be no stable direction. There are small signs that nature is not perfectly symmetrical under time reversal. Certain particle interactions behave slightly differently when time is reversed. These effects occur in processes involving some unstable particles. The differences are real and have been measured. They show that the fundamental laws contain a small form of time asymmetry. It would be tempting to identify this as the source of the everyday arrow. Perhaps cups break because particle physics has already chosen a direction. The known asymmetry is not enough to explain ordinary irreversibility. It affects particular interactions under specific conditions. It does not explain why heat flows from hot objects to cold ones, why memories point backward, or why gas fills a room. The thermodynamic arrow would still need a low entropy past even if these particle processes were perfectly symmetrical. Fundamental time asymmetry may contribute to the full story, but it does not replace entropy. There is also the difference between quantum probability and classical uncertainty. When we shuffle cards, we may not know the final order because the motion is too complicated to track. In principle, the result is fixed by the exact starting conditions. Quantum uncertainty appears to be deeper. The theory may provide only probabilities even when the initial state is known as fully as possible. A radioactive atom, for example, has a certain chance of decaying during a given period. The theory predicts the behavior of many atoms very accurately, but it may not specify the exact moment when one particular atom will decay. When decay occurs, particles and energy are released. A detector may record the event. The environment changes. The result becomes part of history. The decay itself may be random, but the records still form in one direction. Randomness does not reverse the arrow. It creates unpredictable events within it. A future event may be uncertain, while a past recorded event is fixed in the available evidence. This is another reason quantum mechanics feels directional in practice even when its basic evolution is reversible. Measurement turns possible outcomes into stable records for observers. The difference between possibility and record follows the growth of entropy. Quantum experiments can sometimes reverse processes that seem irreversible. Scientists can manipulate small systems so that lost information reappears. They can make particles retrace aspects of their earlier evolution. They can produce echoes in which a collection of spins returns close to a previous arrangement. These demonstrations are important because they confirm that microscopic laws preserve more information than everyday experience suggests. They do not reverse the entire arrow of time. The experimental equipment must be prepared carefully. External energy is used. The surrounding environment continues increasing in entropy. The scientists remember performing the reversal. A small system returns near an earlier state because a larger system has been arranged to make it happen. This is like repairing a cup. The object may resemble its earlier condition, but the universe has not returned to the earlier moment. Quantum reversals show that irreversibility depends on scale, control, and interaction with the environment. For a few well-isolated particles, reversal may be possible. For a warm object containing enormous numbers of particles, exact reversal is beyond realistic control. For the entire universe, there is no larger laboratory available to prepare the reversal. This brings us back to the difference between fundamental laws and emergent behavior. At the fundamental level, many quantum processes do not care strongly about the direction of time. At the level of measurements, environments, and observers, a clear arrow appears. The transition between those levels is not a minor detail. It may be the place where the experienced world acquires its history. A quantum state becomes entangled with its surroundings. Alternatives stop interfering. Information spreads. Records form. Entropy increases. Observers remember one outcome and not the unrealized possibilities. The sequence produces the ordinary sense that something happened. Before the record, there are probabilities. After the record, there is evidence. That does not prove that consciousness creates reality. A detector can form a record without a person watching it. A particle leaves a track in material. A molecule changes after an interaction. The environment can store information long before anyone examines it. Consciousness enters later as another physical system that becomes correlated with the record. The observer sees the detector, forms a memory, and joins the same chain of interactions. This is why placing a person at the center of quantum measurement creates unnecessary confusion. The important event is not necessarily awareness, it is the physical spread of information. A measurement is any interaction that creates a stable correlation between a system and a record. Once the record has spread widely enough, reversing it becomes practically impossible. The arrow of time at the quantum level may therefore be less about particles choosing forward motion, and more about information becoming difficult to recover. Information that begins locally becomes distributed across the environment. The details still exist in the total quantum description, but no ordinary observer can gather them. This resembles heat. Energy is conserved, yet useful energy decreases as it spreads. Quantum information may be preserved while becoming inaccessible in practice. The universe does not necessarily destroy the past. It disperses the information needed to reconstruct it completely. We retain only partial records. A detector shows one outcome. A memory preserves part of an event. A photograph captures one view. The rest becomes mixed into the environment. This is enough to create a stable history. Quantum physics therefore gives two different impressions of time. The isolated equations often look reversible. They allow a quantum state to evolve forward or backward. Actual events occur in environments where systems interact. information spreads and entropy increases. Those processes give a practical direction that is as dependable as any broken cup. The tension between these views leads to the final question. Is the direction of time built into reality at its deepest level, waiting to appear whenever matter interacts? Or is it a large-scale pattern that emerges only because the universe began in a special state? The answer may depend on what we mean by time itself. If time is fundamental, its direction may need a fundamental explanation. If time emerges from change, information, and relationships, then its direction may emerge with it. To decide between those possibilities, we need to separate two ideas that everyday language usually combines. Time can exist without having a preferred direction, and a direction can appear without being written into every microscopic law. The next step is to ask whether the arrow is one of the basic ingredients of the universe, or whether it develops only when countless reversible events are viewed together from inside a world filled with records. The difference between fundamental and emergent properties is easier to understand through familiar examples. Temperature feels like a basic feature of an object. A cup of tea is hot, a window is cold, and bath water is sometimes judged through a careful process involving 1 foot and immediate regret. Yet an individual molecule does not have a temperature in the ordinary sense. A molecule has motion. It can move, rotate, vibrate, and collide with other molecules. Temperature appears when a large number of molecules are considered together. It describes the average behavior of the group. Temperature is real. It can be measured, predicted, and used to explain physical changes. It can burn a hand or freeze a pond. Still, it is not fundamental in the same way that the molecules and their motions are fundamental within that description. It emerges from many smaller events. Pressure works in a similar way. A single gas molecule does not create the pressure measured inside a tire. Pressure comes from countless molecules striking the inner surface. Each collision is small. Together, they produce a stable, large-scale property. A wave on the ocean is another example. The wave travels across the surface, but the water itself mostly moves in local patterns. No single water molecule carries the entire wave from one side of the sea to the other. The organized motion emerges from the behavior of many molecules. The direction of time may belong to this same category. At the microscopic level, many physical processes can run forward or backward. At the large scale, events become strongly one-directional. Heat spreads, records form, causes produce effects. The universe develops away from its low-entropy beginning. Perhaps no individual particle carries the arrow of time. The arrow may appear only when vast numbers of particles interact under particular starting conditions. That would make time's direction emergent. Time itself and the direction of time should be kept separate. A physical theory may include a time variable while allowing events to occur equally well in either direction. The theory can place events in an order without choosing which end should be called the future. A road has two directions. Its existence does not decide which way a traveller must drive. In much the same way, time may provide an ordering of events while entropy determines the direction experienced by observers. The fundamental laws would supply the road. The condition of the universe would determine the traffic. This view fits much of what we have seen. A small, isolated system can behave reversibly. A large system interacting with an environment develops irreversible behavior. Information spreads into many degrees of freedom, and recovering it becomes overwhelmingly difficult. The arrow becomes stronger as the system grows. That pattern is typical of emergence. The large-scale property is weak or absent among the smallest components, then becomes stable when enough components interact. One molecule does not have a meaningful temperature. A large collection does. One particle does not clearly display thermodynamic time. A universe full of interacting matter does. An emergent arrow would not be an illusion. Temperature is not an illusion simply because it comes from molecular motion. A fever remains unpleasant even after someone explains statistical mechanics. Emergent properties are real at the level where they operate. The arrow of time governs engines, stars, living organisms, memories, and every ordinary event. It does not need to be written into each microscopic law to have genuine physical consequences. The harder question is whether the emergence can be explained completely. Saying that entropy increases because high entropy states are more probable answers only part of the problem. A system moves toward more probable states if it begins in a less probable one. Why did it begin there? A box of gas spreads after a divider is removed because the gas started on one side. The later mixed condition is common, while the earlier concentrated condition is special. If the gas had always been evenly spread, there would be no visible process and no local arrow created by its expansion. The universe presents the same difficulty on a much larger scale. Its early state had very low gravitational entropy. Matter was smooth enough to allow galaxies, stars, planets, and black holes to form later. The arrow emerges because the starting condition was special. Probability explains the movement away from that condition. It does not explain why the condition existed. This is where an apparently simple statistical answer reaches the edge of cosmology. One proposal is that the low-entropy beginning is simply a basic fact. The universe started that way, and no deeper explanation is available. Physics already contains quantities and conditions that may need to be accepted before predictions can begin. Perhaps the initial state of the universe belongs to that category. This answer is possible, though not especially satisfying. It resembles asking why a book begins with a particular first sentence, and being told that the sentence is there because it is the first one. Scientists usually look for a deeper pattern. Another possibility is that a fundamental law selected the low-entropy beginning. The law might require the universe to start in a smooth condition. If such a law exists, the arrow would still emerge through entropy. But the reason it can emerge would be fundamental. The distinction becomes less sharp. The direction would not appear directly in each microscopic interaction, yet the basic rules of the universe would guarantee the special boundary needed to create it. A third possibility is that our universe is part of a much larger structure. Perhaps many regions or universes exist with different conditions. Observers appear only in regions where entropy can increase, because life requires energy flows, stable records, and a long period of organized change. In that case, we observe a low-entropy past because only universes with such a past can contain observers asking about it. This kind of reasoning is called selection. It does not show that other universes exist, and it does not fully explain how the larger structure began. It suggests that our location may not be typical. A person living in a warm house should not be surprised that the temperature is suitable for human life. Houses with completely unsuitable conditions tend to have fewer people sitting inside them discussing thermodynamics. The comparison is simple, but the cosmic version is difficult to test. There are also models in which the universe has two directions of time. Imagine a special low entropy condition in the middle rather than at one end. Entropy increases away from it in both temporal directions. Observers on one side would call their direction of increasing entropy the future. Observers on the other side would do the same in the opposite direction. Each group would remember the low entropy condition behind them. Neither would experience time as running backward. From a larger viewpoint, the universe would have two arrows pointing away from the same boundary. This idea shows that the direction of time may depend on where an observer stands within the complete structure. Past and future could be local labels tied to entropy, rather than universal labels attached permanently to the ends of time. There is no clear evidence that our universe has such a second side. The model remains speculative, but it helps separate time from its direction. A timeline could extend both ways while observers on different regions experience different arrows. Cyclic models create another possibility. The universe might pass through repeated stages of expansion and contraction. A simple picture of cycles suggests that time would repeat. The universe expands, contracts, and begins again. Events might return in the same order. Realistic cycles are more difficult because entropy tends to increase. Each cycle would inherit the entropy produced by the previous one. the universe would not return to exactly the same state. A repeated expansion would be a new event, not a replay. Some models try to dilute entropy during periods of extreme expansion, or place each cycle in a larger structure. Whether these ideas can produce a complete and testable account remains uncertain. They demonstrate how difficult it is to explain a low-entropy boundary without placing another unexplained condition behind it. Quantum gravity may eventually change the question. If time itself emerges from a deeper quantum description, asking what happened before the beginning may be like asking what lies north of the most northern point. The ordinary concept may stop applying. A theory without fundamental time could describe the universe through relationships among physical states. Time would appear only within certain approximations, once some parts of the system act as clocks for others. Its direction might then emerge from the pattern of correlations. One part of the universe contains records of another. Entanglement spreads. Entropy increases relative to an internal clock. Observers experience these changes as a sequence. Under this view, the deepest level of reality would not contain a moving present or a universal flow. It would contain a structure from which experienced time develops. The idea is difficult because every explanation we give is expressed in temporal language. We say time emerges, which sounds like there was an earlier stage when time had not emerged. That wording may be misleading. Emergence need not occur as an event in a deeper time. It can describe the relationship between two levels of explanation. Temperature does not appear at a particular moment after molecules have spent some time without it. Temperature is available whenever enough molecules are described collectively. Time might be similar. The fundamental structure does not wait for time to begin. Certain relationships within that structure can be described effectively as temporal. The arrow would then be a pattern inside those relationships. Some approaches connect this pattern with entanglement. A relatively simple quantum state can develop into a more entangled state. Information that was once local becomes distributed across many systems. Observers form memories along that direction because their brains become correlated with events. Measuring devices create records. Environments copy information. The direction of growing correlation becomes the experience future. This resembles the thermodynamic account, but it uses quantum information as the underlying language. Entropy and entanglement are closely related in many quantum systems. Both concern how information is distributed and how many states are compatible with what an observer can measure. The hope is that a deeper theory will show why space-time, gravity, entropy, and information fit together. Black holes provide strong reasons to suspect such a connection. They have entropy, they have temperature, they can emit radiation. Their behavior links gravity, quantum theory, and thermodynamics. The amount of information associated with a black hole appears to depend on the area of its boundary rather than the volume inside. This has led to the suggestion that information in a region of space may be represented on its boundary. If that idea applies more broadly, space-time itself might emerge from patterns of quantum information. Time's direction could then arise from changes in that information structure. This remains an active area of research. There is no accepted final account. Black holes show that the subjects are connected, but they do not yet tell us exactly how the arrow begins. Another option is that time's direction is fundamental after all. Certain particle interactions do not behave exactly the same under time reversal. Experiments have found small differences between processes and their time-reversed versions. This proves that nature contains some fundamental temporal asymmetry. Could that asymmetry eventually explain the direction of everything? At present, the answer appears to be no. The known effect is too limited. It does not explain why heat spreads through a room, or why a brain remembers breakfast instead of tomorrow's lunch. Even in a universe without that particle asymmetry, entropy could still increase from a low-entropy beginning. Fundamental time asymmetry and the thermodynamic arrow are therefore different problems. They may be connected in a complete theory, but one cannot simply replace the other. The known asymmetry also raises a broader point. The microscopic laws are not perfectly indifferent to time in every situation. The statement that physics looks the same forward and backward is an approximation that works for many processes, not an absolute rule covering all of nature. A complete answer may combine several sources of direction. The low-entropy beginning may produce the thermodynamic arrow. Quantum measurement may spread records. Cosmic expansion may support the growth of structure. Fundamental particle effects may add a small built-in asymmetry. These different contributions could reinforce one another without sharing one simple cause. Human experience adds another level. The feeling that time flows is not identical to the physical arrow. Entropy can increase without anyone sensing a moving present. A camera records events, but it does not appear to experience them. A rock changes over time without becoming impatient. Conscious brains process information in sequence. Attention moves. Memories are updated. Expectations are compared with new signals. This creates the personal sense of a present moment advancing. The physical arrow explains why memory and anticipation point in different directions. It may not fully explain why awareness feels located at a moving now. Some philosophers and physicists argue that the flow of time is a feature of consciousness rather than the external universe. In the block universe view, every event in space-time exists as part of one complete structure. Past, present, and future are not created one after another. They are different locations in space-time. An observer's life forms a path through that structure. Each stage contains memories of earlier stages but not later ones. That arrangement produces the local experience of passage. Nothing needs to move through time from outside. The sense of flow comes from how information is arranged along the observer's path. This view fits relativity, which does not provide one universal present shared by everyone. Observers moving differently can disagree about which distant events are happening now. If there is no single cosmic present, the idea that one moment becomes real everywhere at once is difficult to maintain. The block universe removes that problem by treating all space-time events as equally part of reality. It also creates discomfort. The future seems fixed within the structure. Choices appear to be already located in space-time. Supporters reply that a choice can still be real, even if it belongs to the complete structure. The decision is made by the person according to their thoughts, values, and circumstances. Knowing that the event has a location in space-time does not make it causally irrelevant. A road shown on a map still contains real turns for the driver. Others prefer presentism, the idea that only the current moment is real. The past no longer exists, and the future does not yet exist. This matches ordinary experience, but it is difficult to combine with relativity because different observers do not agree on one universal current moment. There are more complicated views in which reality grows as new events occur, or in which the present is local rather than global. None has achieved complete agreement. The debate shows that several questions are often hidden inside the phrase direction of time. Why does entropy increase? Why do records point toward the past? Why do causes precede effects? Why does the universe have a low entropy beginning? Why does conscious experience feel as if the present moves? These questions are related, but one answer may not solve all of them. Entropy gives the most established explanation for everyday irreversibility. A low-entropy past allows systems to move toward more probable states. Energy spreads, records form, and memories accumulate. Cosmology places that arrow within the history of an expanding universe. Quantum physics shows that the underlying laws can preserve information and remain largely reversible. Relativity removes the idea of one universal clock and turns time into part of space-time. Consciousness adds the experience of passage. A complete theory would need to show how these levels fit together without confusing one for another. At present, the safest conclusion is that the direction we experience is mostly emergent. It is not carried by clocks. It is not a force pushing objects into tomorrow. It does not appear strongly in every microscopic interaction. It becomes clear when large systems begin in special conditions and interact with their surroundings. The arrow is statistical, but that does not make it weak. Statistical laws can be among the most reliable laws we know. There is a statistical chance that air molecules could gather into one corner of a room. No sensible person keeps an emergency breathing plan for that possibility. There is a statistical chance that a broken cup could reassemble through random motion. Waiting for it would be a poor use of the kitchen. Large numbers turn probability into practical certainty. Time's direction is dependable because the universe contains enormous numbers of particles, and because its low-entropy past gives them a shared orientation. Whether that low-entropy condition came from a fundamental law remains unknown. The final answer may therefore be a mixture. The arrow itself could emerge, while the conditions allowing it to emerge could be fundamental. Temperature emerges from molecules, but the laws governing those molecules are fundamental within the theory. A wave emerges from water, but gravity and molecular interactions make the wave possible. Time's direction may emerge from entropy, information, and records, while a deeper law sets the structure of the universe in which those processes occur. Finding that law would require a successful theory joining quantum mechanics, gravity, and cosmology. It would also require evidence. A satisfying idea is not enough. Physics must connect the idea to observations or experiments. The earliest universe may contain clues in ancient radiation, the distribution of galaxies, gravitational waves, or other records not yet measured precisely enough. Black holes may reveal how information and space-time are related. Quantum experiments may show how irreversible behavior develops from controlled interactions. Each result adds a piece without yet completing the picture. For now, the direction of time is understood well enough to explain why coffee cools, why memories point backward, and why a cup falls before it breaks. It is not understood well enough to explain why the universe began with the exact conditions needed for any of those things to happen. That gap is not a failure of science. It is a clear statement of where the explanation ends. Science often advances by turning an obvious fact into a difficult question. People saw objects fall long before gravity was described. They saw stars long before learning what powered them. Everyone experiences time's direction, yet its origin remains open. The familiar one-way movement of life may come from a condition established near the beginning of the cosmos. Every memory you form, every object that cools, and every sound that spreads may be connected to that ancient state. A small event in a room carries the history of the whole universe within its direction. The cup falls rather than rises because gravity acts on it. It breaks rather than assembles because the later state is more probable. You remember the sound because the event changes your brain. The record forms because information spreads. All of those processes point away from a low-entropy past. The arrow is not visible as an object, but its effects are everywhere. It is present in the difference between preparation and decay. Building something requires selected materials and organized effort. Deterioration can happen through many uncontrolled routes. It is present in the difference between prediction and memory. The past has left records. The future has not. It is present in the difference between a young star with available fuel and an old remnant that has released most of its useful energy. It is present in the difference between a universe capable of forming structure and a distant future approaching equilibrium. Whether we call that direction fundamental or emergent depends partly on the level we choose to describe. At the level of ordinary life, it is fundamental enough that no one can ignore it. At the level of microscopic laws, it appears to be a collective effect. At the level of the universe's beginning, its source remains unknown. Perhaps a future theory will show that time's direction follows inevitably from a deeper principle. Perhaps it will show that many directions are possible, and ours reflects the region we inhabit. Perhaps time itself will turn out to be an approximate description of relationships in a timeless quantum structure. Any of those answers would change how the question is phrased, but none would make everyday time less real. An emergent river can still carry a boat. An emergent temperature can still boil water. An emergent arrow can still shape every life. You began listening at one moment and have reached another. During that interval, sound entered your ears, signals moved through your brain, and new physical records formed. Energy was used. Heat entered the environment. The universe became slightly higher in entropy. There is no need to be alarmed. The increase was modest, and listening quietly is among the more peaceful ways to contribute. The direction was present throughout, even when no clock was being watched. It did not need to announce itself. It appeared in the order of the words, the formation of memories, and the fact that the beginning of this discussion now lies behind you. We may not know whether the deepest laws chose this direction or whether it emerged from the universe's starting condition. We do know that our experience depends on it. Without an arrow, there would be no stable memories, no learning, no development, and no clear separation between cause and consequence. There would be no practical way to tell a story because a story requires one event to provide the conditions for the next. The direction of time allows the universe to have a history. It allows stars to form from earlier gas, planets to form from earlier stars, life to use earlier energy, and minds to remember earlier events. It allows the present to contain evidence, and the future to contain possibilities. For tonight, that may be the most useful answer. Time gets its direction from the growth of entropy, supported by a low-entropy past whose deeper origin remains one of physics' major unanswered questions. The direction may not be a basic arrow stamped onto every particle. It may be something the universe produces collectively as information spreads and possibilities become records. Yet once it appears, it becomes the framework within which every ordinary event takes place. The clock beside you will continue to mark changes. The room will slowly exchange heat with its surroundings. Distant stars will release energy, and the universe will keep expanding. Your memories of these words will become less exact with time, though perhaps the main question will remain. Why does the future differ from the past? Because the past began in a special condition, and the universe has been moving away from it ever since. Where that special condition came from is the part of the story still being written, one experiment, one observation, and one careful question at a time. If this calm journey through physics has helped you relax or given you something new to consider, you can leave a like and subscribe to Physics with William. It helps this quiet space reach other listeners who may be looking for science without urgency. For the moment, there is nothing more you need to measure or solve. The direction of time will continue without supervision. The next minute will arrive through the same processes that brought the previous one into memory. Events will occur, records will form, and the present will become another part of the past. Wherever you are listening from, and whatever time your clock now shows, you have moved a little farther along the arrow than when we began. Sleep well, and let the universe handle the rest.